Welcome to The Sleepy Scientist, where the stories of science are told gently, at a pace designed to help you unwind before bed. Tonight's journey drifts across the only place in the cosmos we can truly call home. Earth, the living planet. A world of moving stone, flowing water, restless air, and above all, life. Before we begin, I'd love to know, where in the world are you listening from? It is always a quiet joy to see the wide map of places where curious minds tune in. If you enjoy these calming explorations, a like and a subscription go a long way. To those already subscribed, thank you sincerely, and if you would be so kind, do click the little bell so you don't miss the next upload. I sometimes worry these videos might end up being too interesting and keep you awake, though if that happens, at least you will drift off with a few new facts resting in your mind. So settle in, let your thoughts slow, and let the steady rhythm of Earth's story carry you. After all, what makes our world more than just a rock floating in space? Earth is unlike any other planet we know. Beneath its thin shell of atmosphere and oceans, it is a restless world that bends, breathes, and shifts. It is not a frozen, silent stone, but a place alive with motion and pattern, where fire and ice, wind and water all shape the surface in ways both violent and delicate. Life itself is entwined with these forces, never separate from them. Every forest, ocean and desert is part of a larger pulse that has been beating for billions of years. To place Earth in context, one must remember that most planets are barren. Many are wrapped in poisonous atmospheres, some are scorched, some are frozen. Yet somehow, against the odds, this small blue world became something different, a world that makes room for rivers, clouds and trees. That mystery is at the heart of tonight's story, and there is something else to share. This video marks the beginning of a new planet series, released every Tuesday, where each world in our solar system will be explored in the same gentle detail. But Earth comes first, for it is the planet that holds all of us. The tale ahead will not be hurried. It will drift through geology and biology, oceans and mountains, and into the deep rhythms that make Earth a living planet. By the end, perhaps you will see this world not simply as a home, but as a breathing companion in the cosmos. Long before there were forests, oceans, or even solid ground to stand on, there was dust. Not the kind that gathers on a bookshelf, but cosmic dust. Tiny grains of matter left behind from older stars that had lived, burned, and exploded into space. The universe is a patient recycler, and Earth's story begins in this vast cloud of material drifting around a newborn sun about 4.5 billion years ago. The sun itself had just ignited, born from a collapsing cloud of hydrogen and helium. Around it, gravity pulled leftover fragments into a rotating disk of gas and rock. Within this swirling environment, bits of dust collided, stuck together, and gradually built into larger and larger clumps. These growing bodies, called planetesimals, were like the construction bricks of worlds. They crashed, merged, and sometimes shattered in a cosmic version of bumper cars where the prize was existence itself. Earth was one of the winners in this celestial contest. Piece by piece it grew as gravity drew more material in. The collisions were far from gentle. Each impact released tremendous heat, and as the infant planet gained mass, the pressure inside increased. Soon, Earth became a molten sphere, glowing hot and restless, its surface more like a bubbling lava lake than a solid world. In this fiery state, heavy elements like iron and nickel sank toward the centre, forming the core. Lighter materials floated upward to create the mantle and the early crust. This natural sorting gave Earth its layered structure, a feature that still defines how it behaves today. The iron heart at its centre would eventually produce the magnetic field that shields the surface from solar radiation, but at the time, the young planet was still vulnerable, still unfinished. The early solar system was not a quiet neighbourhood. Vast numbers of asteroids and comets were still whizzing around, remnants of planet building gone astray. Earth endured a relentless bombardment during its first few 100 million years. Each impact released more heat, sometimes melting parts of the surface all over again. Some of the impacts were colossal, the kind that could reshape continents before continents even existed. One particularly famous collision is believed to have occurred when a Mars-sized body slammed into Earth. The force of the impact blasted huge amounts of debris into orbit, which eventually gathered into a companion we still see every night, the Moon. As the chaos gradually subsided, Earth began to cool. A thin crust solidified over the molten interior, cracked and unstable at first, but slowly hardening. Volcanoes dotted the surface, releasing gases like carbon dioxide, nitrogen, and water vapor into the air. This was the beginning of Earth's atmosphere, though it would have been unrecognizable compared to today's breathable mix. Toxic and heavy, it created a sky tinted more red than blue, a haze of volcanic fumes clinging to a world still in recovery from its violent birth. Meanwhile, comets and icy bodies from the outer reaches of the solar system likely contributed water to the surface. With time, as the crust cooled further, liquid water began to pool in low-lying areas, forming the first primitive oceans. Imagine a world where the ground still glows in patches, yet steaming seas are already spreading across vast basins. The contrast of fire and water defined these early epochs, setting the stage for something remarkable. It is strange to think that the conditions which seemed so hostile were also the conditions that made Earth special. The volcanic eruptions that darkened the sky supplied gases needed for future life. The constant battering from space not only reshaped the surface, but may have delivered vital ingredients like carbon and organic molecules. Even the catastrophic collision that formed the Moon gave Earth stability by steadying its tilt, creating regular seasons rather than chaotic swings. By about 4 billion years ago, the planet was settling into a more balanced state. The crust was thicker and sturdier, oceans covered much of the surface, and the atmosphere, while still alien, was evolving. The greenhouse effect from gases like carbon dioxide kept Earth warm enough to prevent complete freezing, even though the sun was fainter back then. The planet was still restless. Volcanoes rumbled, meteorites still struck, but it was no longer the wild inferno of its youth. This early Earth may have looked desolate compared to the world we know now, yet it had all the raw ingredients necessary for life to eventually arise. Water flowed across newly formed rocks, dissolving minerals and carrying them into oceans. Lightning flashed in the thick skies, providing energy to rearrange simple molecules into more complex ones. Hydrothermal vents at the bottom of the seas gushed mineral-rich water, creating chemical gradients that could be harnessed for primitive reactions. Everywhere, the environment was a chemistry set waiting to be tried. When you picture Earth in those first few 100 million years, do not imagine a finished masterpiece. Instead, think of a canvas still wet with paint, colours bleeding into each other, the shapes only just emerging. The land was not yet green, the air not yet breathable, and the seas not yet teeming with life. But already the elements of the story were in place: the layered core, the protective moon, the restless crust, and the water that would soon cradle life. The origins of Earth are written into every stone and ocean we see today. The iron in the ground beneath our feet, the oxygen we breathe, the water we drink, all are remnants of that distant time when stardust was gathered, melted and shaped into a living planet. Earth began as a fiery sphere of molten rock, born in chaos, but it was precisely that chaos which made it ready for something more. And so, from dust and fire, from collisions and cooling, the stage was set. A planet had formed, one unlike most others, balanced delicately between destruction and creation. What seemed then a hostile world was in truth a cradle, waiting patiently for the first fragile sparks of life to arrive. Beneath our feet, the ground feels solid. Streets, mountains, valleys, all appear fixed in place. Yet the reality is that Earth's surface is anything but still. It is broken into vast slabs called tectonic plates, and these plates are in constant motion, sliding, colliding, and drifting apart as if the planet itself were engaged in a slow, unending dance. Though the pace is glacial, usually just a few centimetres each year, the effects over millions of years are dramatic. Entire oceans open and close, mountains rise from the ground, and continents migrate across the globe like slow-moving rafts. The engine behind this motion lies deep within Earth's mantle. Heat from the core creates convection currents in the semi-fluid rock beneath the crust, slowly churning and dragging the plates along the surface. Imagine the crust as a cracked eggshell floating atop a pot of simmering soup, pushed and pulled by the currents below. The plates themselves are massive, some spanning entire oceans, and they interact at their boundaries in ways that shape much of the world's geography and natural hazards. When two plates move apart, a divergent boundary is formed. Here, molten rock wells up from below to create new crust. The Mid-Atlantic Ridge, for example, is a sprawling underwater mountain range that runs like a seam down the middle of the Atlantic Ocean. As magma rises and hardens, it pushes the continents on either side farther apart. This process is so steady that the Atlantic grows a few centimetres wider every year, slowly increasing the distance between the Americas and Europe and Africa. Where plates collide, the effects are far more dramatic. At convergent boundaries, one plate may be forced beneath another in a process called subduction. As the descending plate sinks into the mantle, it melts, generating magma that can rise to the surface and form volcanoes. The famous Pacific Ring of Fire, a horseshoe-shaped belt of volcanoes and earthquake zones around the Pacific Ocean, is the direct result of subduction. Entire mountain ranges also owe their existence to colliding plates. The Himalayas, home to the highest peaks on Earth, were thrust upward when the Indian plate rammed into the Eurasian plate tens of millions of years ago, and the mountains are still rising today. Then there are transform boundaries, where plates slide past one another laterally. The San Andreas Fault in California is a classic example. Here, the Pacific Plate and the North American Plate grind against each other, producing the kind of stress that can suddenly release as powerful earthquakes. To those living nearby, these boundaries are a reminder that the apparent stillness of the ground is an illusion. Volcanoes and earthquakes may seem destructive, and in the short term they often are. Yet over the long sweep of time, they play essential roles in keeping Earth habitable. Volcanic eruptions bring material from deep within the planet back to the surface, releasing gases that replenish the atmosphere and nutrients that enrich the soil. Some of the world's most fertile lands, such as those surrounding Mount Vesuvius in Italy or the slopes of Mount Fuji in Japan, exist because of past eruptions. Farmers may live with risk, but they also reap the benefits of volcanic renewal. Earthquakes, too, are part of the system's balance. They release the tension built up along faults, preventing even larger ruptures from occurring later. The shaking may last only seconds, but it is the outward sign of colossal forces at work, reshaping landscapes inch by inch. Over time, entire valleys and mountain chains are sculpted by such movements, even if most shifts are too small for humans to notice. Beyond their immediate effects, plate tectonics also perform a subtler yet vital function. They regulate Earth's long-term climate. When rocks at subduction zones are pulled deep into the mantle, carbon locked in sediments is carried with them. Some of this carbon is eventually released again through volcanic eruptions, creating a planetary carbon cycle that has helped keep Earth's climate relatively stable for billions of years. Without this slow recycling system, greenhouse gases might have built up uncontrollably or vanished completely, either of which could have made Earth uninhabitable. The motion of tectonic plates has also guided the course of life itself. As continents drifted, species were separated or brought together, driving evolution in countless ways. The breakup of the ancient supercontinent Pangaea, for example, scattered animal and plant populations to new environments where they adapted and diversified. The distribution of fossils we find today, from identical ferns in South America and Africa to similar reptile remains in Antarctica and India, provides strong evidence of these ancient connections. Without plate tectonics, the tree of life might have grown very differently. It is easy to forget just how recently the idea of plate tectonics was accepted. For centuries, people noticed the curious fit between the coasts of Africa and South America, but it was not until the 20th century that the theory of continental drift gained traction. In the 1960s, new data from ocean floor mapping and paleomagnetism revealed symmetrical patterns of magnetic stripes on either side of mid-ocean ridges, clear proof that seafloor spreading was occurring. From these insights, the modern theory of plate tectonics emerged, transforming our understanding of Earth as a restless dynamic system. Standing on solid ground, it may feel unsettling to imagine that the land beneath us is riding atop vast moving slabs, but it is precisely this motion that has created the landscapes we love and depend on. The jagged peaks of the Andes, the lush valleys of Indonesia, the island chains of the Pacific, and even the fertile plains of Central Europe are all products of Earth's shifting crust. Without it, the world would be a flat, stagnant place, far less welcoming to life. Next time you see a mountain range on the horizon or walk along a coastline, remember that these features are not fixed. They are the result of millions of years of tectonic motion, still unfolding beneath your feet. The crust may appear quiet, but it is always on the move, slowly redrawing the face of the planet. Earth's surface is a living, breathing mosaic of drifting plates, a restless shell that has shaped not only the land itself, but the very story of life that unfolds upon it. Deep beneath the continents and oceans lies a realm we will never see directly, yet it is one of the most important parts of Earth. At the centre of the planet is a core of iron and nickel, divided into a solid inner sphere and a liquid outer shell. The inner core is squeezed to such pressures that despite its blistering heat, it remains solid. Around it, the outer core churns like a slow, restless ocean of molten metal. This movement is not random. It creates electric currents, and those currents generate something extraordinary, a vast magnetic field that stretches far into space. This invisible shield, known as the geomagnetic field, is one of the main reasons Earth is so hospitable. Without it, life as we know it would have struggled to take hold. The sun constantly blasts out a stream of charged particles, the solar wind, which rushes across the solar system at tremendous speeds. On planets without magnetic protection, such as Mars, this solar wind strips away atmospheres, eroding them until little is left. But on Earth, the magnetic field deflects most of these particles, steering them safely around the planet. It is like an umbrella, invisible yet essential, keeping the worst of the storm at bay. The scale of this shield is immense. It extends tens of thousands of kilometers into space, forming a protective bubble called the magnetosphere. The boundary of this bubble is sculpted by the constant pressure of the solar wind. On the sun-facing side it is pushed inward, while on the night side it stretches out into a long tail that trails behind the planet. Within this shield, life can breathe, oceans can endure, and the atmosphere can remain intact. Still, not all solar particles are turned away. Some manage to slip past and spiral down along the magnetic field lines toward the poles. When they collide with atoms high in the atmosphere, they set them glowing, creating shimmering curtains of colour known as auroras. These displays are most often seen in high-latitude regions, where the magnetic field channels particles toward the poles, painting the night sky with greens, purples and reds. For centuries, people saw these lights as mysterious omens, as breath from the gods, or as spirits dancing above the horizon. Today, we know they are signs of Earth's magnetic shield at work, a visible reminder of the planet's deep inner workings. The auroras are sometimes described as Earth's breathing lights, flickering and flowing as though the planet were inhaling and exhaling. Their beauty hides their violent origins, for each glowing arc is the product of solar storms colliding with Earth's defences. During periods of high solar activity, when the sun releases great bursts of plasma known as coronal mass ejections, the auroras can spread much farther from the poles. At the same time, the magnetic field can be disturbed, creating geomagnetic storms that ripple through power grids and communication systems. In this way, Earth's shield is not only a silent protector, but a dynamic system, one that can be rattled by the sun's moods. The story of the geomagnetic field is also a story written in stone. As lava cools and solidifies into rock, the iron-bearing minerals within align themselves with the magnetic field of the time, like millions of tiny compass needles frozen in place. By studying these rocks, geologists have discovered that Earth's magnetic field has not always looked the way it does now. It has flipped many times, with the north and south magnetic poles trading places. These reversals happen irregularly, sometimes separated by hundreds of thousands of years, sometimes by millions. The last major reversal occurred about 780,000 years ago. While such events may sound dramatic, there is no evidence that they cause extinctions or disasters. Instead, they are another reminder that Earth's shield is alive, constantly shifting and evolving. Even in its present state, the field is not perfectly stable. The magnetic North Pole is wandering at a rate of several tens of kilometers per year, drifting from Canada towards Siberia. Scientists track its position carefully, as navigation systems depend on knowing its location. Beneath the surface, swirling flows of molten iron in the outer core are responsible for these movements. It is a reminder that the shield is a product of fluid motion, not a rigid structure. The importance of Earth's magnetic shield becomes clear when we compare our planet to its neighbours. Mars, for example, once had rivers and perhaps lakes on its surface, but without a strong magnetic field to protect its atmosphere, the solar wind gradually stripped it away. Today Mars is cold and dry, its air thin and fragile. Venus, meanwhile, is shrouded in thick clouds of carbon dioxide, with surface pressures and temperatures hostile to life. Its lack of a magnetic field means that solar radiation directly interacts with its atmosphere, helping to create the harsh environment we see today. Against this backdrop, Earth's magnetic bubble is a rare and fortunate feature. It is worth pausing to consider just how delicate this balance is. The magnetic field depends on the movement of molten metal in the outer core, which in turn depends on the heat flowing outward from the inner core and mantle. If the core were to cool completely and the motion were to stop, the shield would fade. Without it, our atmosphere would be left vulnerable to the solar wind. Life, if it could survive at all, would be forced to adapt to conditions very different from those we know. Thankfully, the core still churns, and it is expected to continue doing so for billions of years. Beyond its practical role, the magnetic field has shaped human imagination. Compasses, which align with the field, open the way for navigation across seas and continents. Myths and legends grew from the glow of auroras. Even the idea of Earth as a living world is reinforced by this unseen heartbeat, pulsing from the depths of the core to the skies above. When you stand beneath an aurora, you're not only watching lights in the sky, you're witnessing the interaction of two giants, the Sun and Earth, locked in an endless exchange of energy. The shimmering waves are a signature of the planet's resilience, proof that what happens deep within can ripple outward into space and into our own sense of wonder. Earth's magnetic shield is more than just protection. It is a reminder that our world is alive in ways that stretch from its iron heart to the farthest edges of its sky. Water is the quiet traveller that never truly rests. It evaporates from oceans, lakes and leaves, drifts into the sky as vapour, gathers into clouds, and then falls again as rain or snow. Once it touches the ground, it seeps into soil, trickles into rivers, or carves channels through rock before finding its way back to the sea. This endless circulation is the water cycle, Earth's circulating veins, carrying energy and nourishment through every corner of the planet. It is one of the reasons Earth is alive with motion, and one of the reasons life could take root and flourish here. The beauty of the water cycle lies in its constant transformation. A droplet may spend days floating in the atmosphere, months coursing through a river, or centuries locked inside a glacier. Along the way, it shapes the land and sustains organisms. When the sun warms the oceans, molecules of water gain enough energy to escape into the air. This invisible vapor rises, cooling as it climbs higher until it condenses into clouds. From there, gravity eventually draws it back down, sometimes gently as drizzle, sometimes violently as a thunderstorm. Each raindrop that falls carries with it a history of travel, and when billions fall together, they transform landscapes. Rivers, powered by this returning rainfall, are among nature's finest sculptors. Over time, a steady flow of water can carve valleys, dig canyons, and transport mountains worth of sediment toward the sea. The Grand Canyon in Arizona is a striking testament to what rivers can achieve given millions of years. In more modest ways, every stream that meanders through a meadow or cuts across farmland is reshaping the ground, redistributing nutrients, and creating habitats for countless organisms. Without rivers, Earth would be a far harsher, less fertile place. Yet it is the oceans that dominate the story of water. Covering more than 70% of Earth's surface, they act as immense heat engines, absorbing energy from the sun and redistributing it around the globe. Currents such as the Gulf Stream move vast quantities of warm water northward, moderating climates that would otherwise be far colder. Without the ocean's ability to store and transport heat, weather patterns would be far more extreme, and many regions of the planet would be uninhabitable. The seas also act as a reservoir for carbon, dissolving and storing it in ways that help regulate Earth's atmosphere. Life's reliance on liquid water is not a coincidence. Water is a universal solvent, able to dissolve more substances than almost any other liquid. This property allows it to carry nutrients within living organisms and across entire ecosystems. Inside cells, water provides the medium in which biochemical reactions occur. It cushions and supports tissues, transports oxygen and carbon dioxide, and helps regulate temperature. Without liquid water, the machinery of life simply cannot run. The fact that Earth holds liquid water at all is a delicate balance. Positioned in what astronomers call the habitable zone, Earth is at just the right distance from the Sun for surface temperatures to allow water to remain fluid. Too close, and it would boil away like it did on Venus. Too far, and it would freeze solid as on Mars. Earth also has an atmosphere thick enough to maintain pressure, preventing liquid water from evaporating instantly. This balance has been sustained for billions of years, thanks in part to the carbon cycle and plate tectonics, which recycle gases and regulate climate. Beyond practicality, water is also a source of wonder. Standing on a coastline, watching waves crash endlessly against rock, it is impossible not to feel the power of this restless element. The ocean tides, driven by the pull of the moon, give the seas a rhythm like a heartbeat, rising and falling in cycles that shape coastal ecosystems. In polar regions, frozen water locks away vast reserves of Earth's fresh water, releasing it slowly as glaciers melt into rivers. In deserts, water is the most precious treasure, appearing only in rare storms that transform barren landscapes into bursts of colour. Water also links every part of the biosphere together. The same molecule that once evaporated from the Pacific may later fall as rain in the Amazon or freeze as snow on the Himalayas. Plants draw it upward from the soil and release it into the air through tiny pores in their leaves, creating invisible rivers of moisture that feed clouds and rainfall elsewhere. Animals carry it within their bodies, drinking and excreting, passing it along through food chains. In this way, the water cycle is not just a physical process but a biological one, connecting forests, oceans, and skies in an unbroken circuit. The importance of water to human civilization cannot be overstated. Cities and cultures have flourished along rivers such as the Nile, the Tigris, and the Yangtze. Agriculture depends on rainfall and irrigation, while trade and exploration have long relied on the oceans. Even today, with advanced technology, societies remain deeply tied to the rhythms of the water cycle. Droughts can destabilize regions, floods can reshape economies, and the availability of clean fresh water remains one of the great challenges of our time. For all its familiarity, water continues to surprise. Scientists studying distant moons and planets often search first for evidence of water, since its presence is the strongest hint that life could exist there. The discovery of subsurface oceans on moons like Europa and Enceladus has reignited questions about whether Earth is truly unique. Yet even if life exists elsewhere, the scale and stability of Earth's water cycle make it extraordinary. Few, if any, worlds can boast oceans stretching across thousands of kilometers, glaciers that wax and wane with the seasons, and rivers that etch valleys over eons. It is no exaggeration to say that water shapes nearly everything about Earth's character. From the mountains that rivers wear down, to the fertile soils they leave behind, to the clouds that cool and shade the land, water is both artist and caretaker. Its circulation distributes energy, regulates climate, and sustains the fragile networks of life that cover the planet. Without it, Earth would be as barren as the moon, a world of rock with no pulse. When you drink a glass of water, it is worth remembering that those molecules have been on a journey longer than any story we could tell. They may have once drifted in a prehistoric ocean, fallen as rain on a dinosaur, frozen into a glacier during the last ice age, and now find themselves in your hand. Every drop has travelled across time and space, cycling endlessly through Earth's veins. Water does not just run through Earth, it is Earth's circulation, its silent rhythm. In its endless cycle of rise and fall, of carving valleys and carrying life, water is the element that ties this restless planet together. Beneath the restless surface of the sea lies a hidden system that never sleeps. While waves crash on shorelines and tides rise and fall with the pull of the moon, the real engine of the ocean is quieter, deeper, and far more powerful. This is the circulation of currents that shuttle heat, salt, and nutrients around the globe, a vast conveyor belt that acts like the heartbeat of Earth. Without it, climates would collapse, life in the seas would dwindle, and the delicate balance that makes our planet habitable would falter. At first glance, the ocean seems like an enormous reservoir of still water, but in reality it is alive with motion. Surface currents are driven by winds, sculpted by the rotation of the planet, and deflected by the shapes of continents. These currents trace loops across entire oceans, forming great gyres that move clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. The Gulf Stream, for example, carries warm water northward from the Caribbean across the Atlantic, delivering heat to Western Europe and giving the region a milder climate than its latitude would suggest. Without this steady river of warmth, winters in London or Paris would resemble those of northern Canada. Yet the surface is only part of the story. Far below, in the cold darkness, another current system operates on a planetary scale. This is the thermohaline circulation, driven not by winds but by differences in temperature and salinity. In polar regions, seawater becomes colder and saltier as ice forms, making it denser. This dense water sinks, plunging into the abyss and spreading along the ocean floor. Elsewhere, warmer surface waters move in to replace it, creating a continuous loop. It can take 1,000 years for a single parcel of water to complete this journey, travelling from the surface to the depths and back again. This circulation is not merely a curiosity of physics, it is the thermostat of Earth. By redistributing heat between the equator and the poles, it moderates extremes and stabilises climates. Without the ocean's hidden heartbeat, tropical regions would swelter unbearably, while high latitudes would freeze far more severely. It is this global conveyor belt that helps make Earth's climate relatively stable, allowing life to thrive across such a wide range of environments. The consequences of this system ripple into everyday life. The rains of the monsoons in Asia, the drought cycles in Africa, the gentle summers of Europe, all are influenced by ocean currents. Even fisheries depend on these flows, as currents bring nutrients from the deep back to the surface, feeding the phytoplankton that form the base of the marine food web. If the conveyor belt were to stall or shift dramatically, as scientists fear it could under the pressures of climate change, the effects would cascade across the globe, altering weather, agriculture, and ecosystems. But currents and climate are only part of the ocean's story. Beneath the surface lies an entire world hidden from view, one that is only beginning to be explored. The deep sea, stretching down to depths where no sunlight penetrates, is home to ecosystems as strange as any science fiction tale. At the bottom of the ocean, along mid-ocean ridges and subduction zones, hydrothermal vents spew superheated water rich in minerals. To human eyes, it would appear as a hostile alien place. Yet around these vents thrive dense communities of life. Here, instead of sunlight, the basis of life is chemistry. Microorganisms use the energy from minerals and gases in vent water to produce food in a process called chemosynthesis. Around them cluster giant tube worms with blood-red plumes, ghostly crabs, and bizarre fish adapted to total darkness. These ecosystems are among the most isolated on Earth, yet they flourish, demonstrating that life can take hold even in the most extreme conditions. Some scientists speculate that life on Earth may have begun in places like these, where the mixing of hot, mineral-rich fluids and cold seawater provided the perfect conditions for complex chemistry. The deep sea also holds vast plains of soft sediment, dotted with creatures that look more like works of art than animals. Transparent jellyfish drift silently. Bioluminescent squid flash and fade like living lanterns. Strange fish with oversized eyes or glowing lures patrol the darkness. Many of these creatures remain unnamed, their biology still mysterious. Each new expedition reveals species that challenge our understanding of how life can adapt. It is a realm where pressure is immense, light is absent, and yet diversity abounds. Even in the open ocean, far from the vents and ridges, unseen currents play vital roles in supporting life. Upwelling zones, where deep, cold water rises to the surface, bring with them nutrients that fertilize the sea. These areas become biological hotspots, feeding vast schools of fish, flocks of seabirds, and migrations of whales. The life we see at the surface, the splashes of dolphins, the diving of seabirds, the shimmer of anchovy shoals, is sustained by invisible processes deep below. To think of the ocean as a thermostat is accurate but incomplete. It is more like a circulatory system, constantly pumping energy and nutrients from one place to another. The heartbeat of the ocean is slow, steady, and vast. But without it, Earth would be a very different world. The seas are not passive basins of water. They are active agents, shaping climate, geology, and biology alike. Human history has been tied to the rhythms of the ocean for as long as people have ventured near its shores. Navigation relied on currents and winds. Coastal settlements thrived on fisheries enriched by nutrient flows. Even today, satellites track ocean temperatures and currents to forecast weather, monitor hurricanes, and understand climate patterns like El Niño and La Niña. What happens in the depths of the Pacific can influence rainfall in South America, drought in Africa, or storms across the Atlantic. The more scientists learn about the ocean's hidden systems, the more they realize how delicately balanced they are. Small changes in temperature or salinity can alter currents, potentially slowing the Great Conveyor Belt. Glacial melt from Greenland, for instance, adds fresh water to the North Atlantic, diluting salinity and reducing the sinking of dense water. If this process were to accelerate, the entire thermohaline circulation could weaken, with consequences that would reverberate through every corner of the globe. Yet for all its importance, the deep ocean remains one of the least explored frontiers on Earth. We have sent probes to other planets and walked on the moon, but vast stretches of our own seafloor remain unmapped. The hidden heartbeat of the ocean continues largely out of sight. Silent but essential. It is humbling to realize that the very stability of our climate, the fertility of our seas, and the comfort of our weather all depend on processes we're only beginning to fully understand. Next time you stand by the sea and listen to the waves, consider that beneath those rolling surfaces lies a system older and grander than any human structure. The ocean does not merely sit at the edges of continents. It moves, breathes, and pulses, shaping the world in ways we feel every day. Its currents carry heat like arteries, its depths harbour life in forms strange and beautiful, and its steady circulation keeps Earth within the narrow window where life can flourish. The ocean's hidden heartbeat is the quiet rhythm of a living planet, one that has sustained us for countless generations and will continue as long as its great pulse endures. If you were to rise from the ground and travel upward, leaving behind forests, mountains and clouds, you would notice something surprising. The sky is not endless. The air that sustains us, the familiar blue we see above, is only a thin veil wrapped around the planet. Compared to Earth's size, the atmosphere is no thicker than the skin on an apple. It looks vast from below, but from space, it is a delicate halo, fragile and unique. This thin blanket is divided into layers, each with its own character. Closest to us is the troposphere, the lowest slice of air where weather is born. It extends up about 12 kilometers, a distance less than many daily commutes. Here, clouds form, winds blow, and raindrops fall. It is the layer of storms and sunshine, and nearly all life on Earth depends on it. Above that lies the stratosphere, reaching about 50 kilometers high. Within the stratosphere sits the ozone layer, a shield that absorbs much of the sun's harmful ultraviolet radiation. Without it, life on the surface would face far greater risks, and early organisms might never have flourished. Higher still is the mesosphere, a region stretching to around 80 kilometers above Earth. This is where meteors burn brightly as they streak through the sky, heating up and disintegrating before they can reach the ground. Above the mesosphere is the thermosphere, an extreme environment that extends hundreds of kilometers outward. Here, the air is so thin that individual molecules can reach scorching temperatures when struck by sunlight, even as the region feels cold because there are so few particles to transfer heat. The thermosphere is also where the auroras shine, glowing curtains of light that ripple during solar storms. Finally, at the edge, fading almost imperceptibly into space, is the exosphere. At this altitude, air molecules are so scarce that they can drift away into the void, slipping into the vastness beyond Earth's grip. Though invisible, the atmosphere is a master regulator. It keeps Earth's surface from freezing at night or broiling during the day by trapping and redistributing heat. It acts as insulation, maintaining a balance that allows liquid water to exist. On a planet without such an atmosphere, like the Moon, temperatures swing violently from searing heat in sunlight to bitter cold in shadow. On Earth, the air smooths these extremes, creating a temperate environment where life can thrive. The gases themselves form a careful recipe. About 78% is nitrogen, an element that is relatively inert but essential for building proteins and DNA when fixed into usable forms. Around 21% is oxygen, the gas that fuels our breathing and powers the metabolism of animals. The remaining 1% is made up of argon, carbon dioxide, and trace gases, small in quantity but significant in effect. Carbon dioxide, though less than a fraction of a percent, plays an outsized role in regulating climate. Water vapour, varying from place to place, drives weather patterns and helps control temperature. This particular balance has been refined over billions of years by the activity of life itself. The atmosphere is not just a shield and a thermostat, it is also a stage for beauty. Sunsets glow red and orange because sunlight travels through a thicker slice of air, scattering shorter blue wavelengths and leaving longer hues behind. Rainbows form when sunlight bends and reflects through drops of water. Halos appear around the Moon when ice crystals in high clouds bend light. Even the simple blue of the daytime sky is the result of air molecules scattering sunlight, making short wavelengths more visible. Without the atmosphere, the sky would be black even at noon, and the world would be a far lonelier sight. Despite its power, the atmosphere is fragile. Its total mass is immense, but when spread over the surface of the planet, it amounts to only a thin film. Human activity has shown just how vulnerable it can be. In the 20th century, chemicals released into the air began eroding the ozone layer. The discovery of this thinning shield raised alarm, and global efforts led to restrictions that have allowed the ozone to recover slowly. It was a rare success story in planetary stewardship, proof that awareness and cooperation can mend damage. Yet other challenges remain, especially the build-up of greenhouse gases that trap more heat than Earth can release, slowly warming the climate and disrupting the balance the atmosphere has maintained for so long. It is sobering to realise how finely tuned this system is. A small change in the composition of gases can alter climate patterns across the world. An increase in carbon dioxide leads to melting glaciers, rising seas, and shifting weather. A decrease in ozone can increase rates of skin cancer and harm crops. Every breath we take is part of this interconnected system, every exhale returning carbon dioxide to the air, every inhale drawing in oxygen that plants and microbes have supplied. Other worlds show us how rare Earth's atmosphere truly is. Mars has an atmosphere so thin that its surface is cold and dry, unable to hold liquid water. Venus, in contrast, has an atmosphere so thick with carbon dioxide that surface temperatures soar high enough to melt lead. Compared with these extremes, Earth's air is a miracle of balance, not too thin, not too heavy, but just right. The atmosphere also shapes the story of life in quieter ways. Birds soar on currents of rising air, seeds drift on the wind, and insects use it as their invisible road. The patterns of migration, the cycles of pollination, and even the spread of scents and signals all depend on this unseen medium. For humans, it has become a highway for travel, carrying aircraft across continents and balloons into the stratosphere. The atmosphere is not merely a background to life, it is an active participant in it. To imagine Earth without its atmosphere is to imagine silence. No wind through trees, no clouds drifting overhead, no rain nourishing the soil. The sky would be empty, stars visible even in daylight, but the world below barren. Instead, we live under a thin blue veil that provides air to breathe, warmth to survive, and beauty to inspire. It is fragile, yes, but it is also resilient, shaped by billions of years of interaction between rock, water, and life. Next time you look up and see the soft gradient of the sky, remember that it is not endless. It is a boundary, a thin line that separates us from the vacuum of space, and yet within that line lies the difference between a lifeless rock and a living planet. Earth's atmosphere is more than just air. It is the breath of the world itself. Climate is often thought of as the background music of life on Earth, steady and predictable compared to the daily ups and downs of weather. But across deep time, the tune has shifted, sometimes subtly, sometimes dramatically, shaping the world in ways that ripple through every living thing. Ice has stretched across continents, then retreated. Jungles have expanded into deserts, only to green again when conditions changed. Earth's climate is not fixed. It is a dancer, swaying between cold and warmth, driven by a combination of cosmic rhythms, geological changes, and the living systems it sustains. One of the most striking examples of this dance is the recurring cycle of ice ages. Over the past 2.5 million years, glaciers have advanced and retreated dozens of times, covering vast portions of North America, Europe, and Asia. At the height of the last ice age, about 20,000 years ago, ice sheets more than 3 kilometers thick blanketed much of the northern hemisphere. Sea levels were lower by more than 100 meters, exposing land bridges that allowed animals and humans to migrate between continents. Then, as the planet warmed, the ice melted, seas rose, and ecosystems shifted. Today, we live in an interglacial period, a relatively warm phase between icy expansions, but the memory of frozen landscapes is written into the land itself, carved into valleys and scattered as erratic boulders dropped by retreating glaciers. Yet Earth has also known times when warmth reigned supreme. During greenhouse phases in its history, such as the Cretaceous period around 100 million years ago, there were no polar ice caps at all, temperatures were higher, seas were deeper, and tropical conditions stretched far toward the poles. Forests thrived in regions that are now tundra, and reptiles and early mammals flourished in climates unfamiliar to us today. These swings remind us that climate is not a static state, but part of a much larger cycle of transformation. The causes of these shifts are complex and interconnected. One key factor is the arrangement of continents. When land masses cluster near the poles, ice sheets are more likely to form and persist. When continents drift closer to the equator, warm currents circulate more freely, reducing the chance of global glaciation. Volcanic eruptions also play a role, releasing carbon dioxide that can trap heat, or ash that can temporarily cool the planet by reflecting sunlight. On an even larger scale, variations in Earth's orbit and tilt, the so-called Milankovitch cycles, alter the distribution of sunlight, nudging the planet toward colder or warmer phases. Climate is shaped not just by external factors, but also by internal feedback loops. These loops are like the dancer's partners, amplifying or moderating each move. A classic example is the ice albedo effect. When ice expands, its bright surface reflects more sunlight, cooling the planet further and encouraging even more ice growth. Conversely, when ice retreats, darker ground and water absorb more heat, accelerating the warming. This feedback can turn small changes into sweeping transformations. Another feedback lies in the oceans. Warm water holds less carbon dioxide, so as temperatures rise, more of this gas escapes into the atmosphere, further enhancing the greenhouse effect. These intertwined loops give climate both its stability and its sensitivity. Remarkably, despite these fluctuations, Earth has remained within a range that allows life to persist. This long-term stability is sometimes called the Gaia hypothesis, the idea that Earth behaves like a self-regulating system, with life itself playing a role in maintaining balance. Plants, for example, draw down carbon dioxide through photosynthesis, cooling the climate, while respiration and decay return it to the air. Marine plankton capture carbon in their shells, which eventually sink to the sea floor, locking it away for millions of years. Forests, wetlands, and soils act as reservoirs, modulating the flow of greenhouse gases. Through these processes, Earth has avoided the fate of its planetary neighbours, Venus scorched and suffocated, or Mars cold and barren. Still, self-regulation does not mean immunity. Earth's climate is sensitive to disruptions, and history shows that when the balance tips too far, consequences are profound. About 55 million years ago, during the Paleocene-Eocene thermal maximum, the sudden release of carbon into the atmosphere triggered a spike in temperatures of 5 to 8 degrees Celsius. The oceans acidified, ecosystems shifted, and species migrated or vanished. It took hundreds of thousands of years for the climate to recover. On the other end of the spectrum, during Snowball Earth episodes over 600 million years ago, ice may have covered nearly the entire planet. Life survived in pockets of open water or near hydrothermal vents, but the world was radically transformed. These examples highlight how finely tuned Earth's climate system is and how small changes in inputs can lead to vast consequences. For humans, the climate dance has been both a challenge and a gift. The rise of agriculture around 10,000 years ago coincided with a period of unusual climate stability. Mild, predictable conditions allowed crops to flourish and civilizations to grow. Shifts in rainfall, however, have toppled societies. Droughts contributed to the decline of the Mayan Empire, while colder periods such as the Little Ice Age in the 17th century brought hardship to Europe. Our history is woven tightly into the larger rhythms of Earth's climate. Today, the dance continues, but with a new partner, human influence. By burning fossil fuels, clearing forests and altering landscapes, humans have added unprecedented amounts of carbon dioxide and methane to the atmosphere. These gases amplify the greenhouse effect, nudging Earth's climate toward a warmer state at a speed rarely seen in geological records. The challenge is not that the planet has never been warmer. It has. but that the pace of change is so rapid. Natural systems, including human societies, struggle to adapt when the music shifts too quickly. Still, there is wonder in watching the vast interplay of forces that make up climate. The way clouds drift and reflect sunlight, the circulation of currents that carry heat across the oceans, the seasonal growth and decay of forests, all are parts of a grand choreography. Earth's climate is a dancer that balances on a narrow stage, guided by both external rhythms and internal feedbacks. When you step outside and feel the air on your skin, you're experiencing the result of billions of years of practice, of a planet finding its steps between ice and fire. It is a reminder that while Earth is self-regulating, it is also sensitive, and that sensitivity is what makes the planet both resilient and vulnerable. The dance of climate is ongoing, a performance older than mountains, and we are part of its audience, and now part of its influence. Beneath the grass, forests and fields lies a world so familiar we rarely think about it, and yet so mysterious that scientists are still uncovering its secrets. Soil may look like nothing more than dirt clinging to your shoes, but it is one of the most remarkable layers of Earth. It is the living skin of the planet, a thin, fragile interface between bare rock and the vibrant web of life. Without it, ecosystems as we know them would collapse, crops would wither, and the cycle of life would falter. Soil is created slowly over centuries and millennia through the patient grinding of rock and the equally patient work of life itself. Wind and rain wear mountains down grain by grain. Roots creep into cracks, breaking stone into fragments. As organic material falls, leaves, branches, dead organisms, it mixes with mineral particles, creating a blend that is neither just rock nor just life, but a union of both. This process builds the fertile ground that sustains plants, animals, and humans alike. At first glance, soil seems simple, a mixture of sand, silt, clay, and organic matter. But dig deeper, even just a handful, and you are holding an entire universe. Within that dark matrix live billions of microorganisms, bacteria, archaea, fungi, and protozoa. These tiny residents are the planet's unseen chemists, constantly breaking down material, recycling nutrients, and making them available for plants. A single teaspoon of healthy soil can contain more microbes than there are people on Earth, an invisible community whose activities shape everything from the fertility of fields to the composition of the atmosphere. Fungi in particular weave through the soil like underground threads, forming vast networks known as mycelium. These networks connect to the roots of different plants, allowing them to share nutrients and even signals. Through these fungal highways, a tree in sunlight can pass sugars to a shaded neighbour, or a plant under attack can release chemical warnings that spread to its companions. Some scientists call this the Wood Wide Web, an underground system of communication and cooperation that makes forests more than just collections of individual trees. Roots too are part of this hidden web. As plants grow, their roots explore the soil, branching and twisting in search of water and minerals. In doing so, they create spaces for air and moisture, stabilizing the ground and preventing erosion. Roots release compounds into the soil that attract helpful microbes, forming partnerships that benefit both sides. Legumes such as peas and beans, for example, host bacteria in nodules on their roots that can fix nitrogen from the air, enriching the soil for future plants. These quiet collaborations underpin the fertility of ecosystems and the productivity of farms. Soil is also an enormous reservoir of carbon. Organic matter, once buried in the ground, can remain stored for centuries. Forest soils, grasslands and wetlands all act as carbon sinks, absorbing and holding greenhouse gases that would otherwise warm the atmosphere. At the same time, when soils are disturbed by deforestation or intensive farming, much of this stored carbon can be released, contributing to climate change. The balance between storage and release makes soil one of the planet's most important climate regulators, a role often overlooked because it happens out of sight. The variety of soils across Earth is as diverse as the landscapes themselves. In tropical rainforests, soils are often thin and nutrient-poor because heavy rains wash minerals away, yet the rapid cycling of organic matter sustains lush vegetation. In prairies, deep, rich soils form from centuries of grasses dying back and building layers of organic material, making them some of the most fertile on Earth. Desert soils, sparse and dry, support hardy plants and animals adapted to scarcity. Each type of soil tells a story about the environment it belongs to, its colour, texture, and chemistry, shaped by climate, rock, and time. Human civilizations have always been tied to the quality of soil. The rise of agriculture depended on fertile floodplains such as those of the Nile, the Tigris, and the Indus rivers. Ancient societies thrived when soils were managed carefully, and many declined when soils were exhausted or eroded. Today we rely on soil for the vast majority of our food, whether through crops grown directly in it, or livestock fed on plants it sustains. Yet modern pressures, over-farming, deforestation, and urban expansion threaten to degrade this living skin at an alarming rate. Unlike air or water, which can circulate and renew more quickly, soil takes centuries to form but can be lost in a single season of careless use. Beyond its utility, soil is also a habitat in its own right. Countless creatures, from earthworms to beetles to burrowing mammals, call it home. Earthworms in particular are nature's engineers, aerating the soil as they tunnel and leaving behind nutrient-rich casts. Their activity improves soil structure, making it better at holding water and supporting plant growth. Even the smallest soil dwellers, mites, and nematodes, play roles in controlling populations of microbes and decomposing organic matter. It is an entire ecosystem beneath our feet, humming with interactions too small to notice, but too important to ignore. Soil also connects past and present. Layers of earth preserve the remains of ancient organisms, pollen grains, and even human artifacts. Archaeologists and paleontologists alike turn to soil as a record of history, a layered archive that holds stories of changing climates, shifting ecosystems, and vanished civilizations. Every layer is a page in Earth's diary, waiting patiently to be read. Despite its ubiquity, soil remains underappreciated. People admire towering mountains, vast oceans, or bright skies, but rarely pause to marvel at the dark, crumbly ground beneath their feet. And yet, without it, forests would vanish, rivers would silt, and the very air we breathe would lose its balance. Soil anchors life as securely as gravity anchors our bodies to the planet. It is quiet, yes, but it is also indispensable. Next time you hold a bit of soil in your hand, consider that it's not just dirt. It is a living skin, the meeting place of rock and life, a home for invisible billions, a foundation for every ecosystem on land. Each handful is a reminder of Earth's patience, of the countless years it takes to create, and of the delicate balance needed to sustain it. The ground beneath us is not dead. It is alive, and in its quiet persistence, it keeps the world flourishing. In the beginning, Earth was a place of rock, water, and gas. It was a restless world with oceans forming on its surface, volcanoes venting gases into the sky, and lightning flashing through thick clouds. There was no grass underfoot, no trees swaying in the wind, no animals darting about. Yet within this seemingly barren landscape, something extraordinary was brewing. Life was about to spark, not through a miraculous event in a single instant, but through countless small steps in chemistry, each one nudging Earth closer to becoming a living planet. Scientists believe that the origins of life are tied closely to the oceans. Water is the perfect medium for chemistry, a solvent that allows molecules to move, interact, and combine. In the early seas, simple compounds like methane, ammonia, carbon dioxide, and hydrogen cyanide mingled with water. With energy from lightning strikes, ultraviolet radiation, and volcanic heat, these raw ingredients began to link into more complex molecules. In the 1950s, a famous experiment by Stanley Miller and Harold Urey simulated conditions thought to resemble early Earth. By running sparks through a mixture of simple gases and water, they produced amino acids, the building blocks of proteins. It was a striking demonstration that the leap from chemistry to biology was not an impossible one. The oceans of 4 billion years ago may have been full of these building blocks, amino acids, nucleotides, lipids, each one a small step toward life. But a pile of ingredients does not make a living organism. The crucial question is how these molecules assembled into something organized, something capable of copying itself and evolving. One idea is that life began near hydrothermal vents at the bottom of the sea. These vents spew mineral-rich water, creating natural chemical gradients. In such an environment, molecules could have gathered on mineral surfaces, forming increasingly complex structures. The flow of heat and chemistry may have provided the conditions for simple reactions to become networks of reactions, the first stirrings of metabolism. Another idea is that life's spark came in shallow pools on land, where cycles of drying and wetting concentrated molecules, forcing them into new combinations. Sunlight, evaporation, and storms would have repeatedly broken and reformed bonds, creating a kind of natural laboratory. In either case, the exact location remains uncertain, but what is clear is that Earth provided countless opportunities for chemistry to experiment. With enough time and variation, the improbable became inevitable. Among the earliest breakthroughs was the appearance of molecules that could carry information. Today, DNA holds the instructions for building every living thing, but many scientists think RNA came first. RNA is capable not only of storing information, but also of catalyzing reactions, acting like both a blueprint and a tool. In a world before proteins and enzymes, RNA may have been the versatile molecule that allowed life to gain a foothold. Small RNA molecules that could copy themselves, even imperfectly, would have had an enormous advantage. Errors in copying, mutations, would have created variety, and natural selection could begin to shape which forms persisted. The next leap was the formation of cell-like compartments. Life needs boundaries to maintain order, to separate itself from the chaos of the outside world. Simple fatty molecules can naturally assemble into bubbles or membranes, enclosing pockets of water. Within these tiny enclosures, molecules could concentrate and interact, shielded from dilution in the vast ocean. These protocells may have been the first step toward true cellular life, containers where chemistry began to take on the qualities of biology. From there, life's machinery grew more elaborate. Networks of reactions formed rudimentary metabolisms, extracting energy from the environment. Molecules became more specialized, some storing information, others speeding up reactions, others building structures. Over millions of years, these simple systems gave rise to the first true cells, organisms capable of growing, dividing, and evolving in a sustained way. They were microscopic, fragile, and incredibly simple by modern standards, yet they were the ancestors of every living thing that followed. For a long stretch of Earth's history, life remained at this single-celled stage. Bacteria and archaea dominated the oceans, multiplying and diversifying into countless forms. They adapted to extremes of heat, salt, and acidity, colonizing places from volcanic vents to shallow seas. Some evolved the ability to capture energy from sunlight, a development that would eventually transform the entire planet. When cyanobacteria began photosynthesizing, they released oxygen as a byproduct. At first, this oxygen reacted with iron in the oceans, staining the seas with rust-colored deposits. But over time, it accumulated in the atmosphere, setting the stage for more complex life forms to emerge. Looking back, it is astonishing how much had to fall into place for life to begin. The right chemicals had to be present. The right sources of energy had to drive reactions. Molecules had to find ways of organizing, copying, and protecting themselves. At each step, the odds may have seemed small, but the vastness of time and the sheer scale of the planet's chemistry meant that experiments were running everywhere, all the time. Earth was, in effect, a giant laboratory, and out of its restless reactions came something entirely new, self-sustaining, evolving life. This origin story reminds us that life is not separate from the planet. It is a product of it. The molecules that once swirled in the atmosphere and oceans became the proteins, DNA, and cell membranes of living creatures. The boundary between non-living and living is not a sharp line, but a gradient, a gradual rise in complexity until, at some point, the balance tipped. Once it tipped, evolution took over, guiding life into endless variations. The exact details of how life first began remain one of science's great mysteries. Perhaps multiple pathways were attempted, with only one line surviving. Perhaps life's spark was fragile at first, nearly extinguished many times before becoming robust. What matters is that it did happen, and from those humble beginnings, an entire biosphere arose. Every creature alive today, from the tiniest bacterium to the largest whale, can trace its lineage back to those first sparks of chemistry in Earth's ancient seas. When we look at Earth now, rich with forests, coral reefs and teeming grasslands, it is easy to forget that everything began with simple molecules bumping into each other in a watery world. Life was not handed to Earth. It was built here, step by step, from the raw materials of a young planet. Against odds that seemed staggering, Earth's chemistry found a way. In that sense, our planet is proof that the line between physics, chemistry and biology is not a wall, but a continuum. Out of rocks, gases and water, out of energy from lightning and vents, came the ability to grow, to change, and to remember. Earth's story is not just one of a planet, but of a chemistry experiment gone spectacularly right. Billions of years ago, Earth's atmosphere was unrecognizable. It was a mix of nitrogen, carbon dioxide, methane, and other gases. But one ingredient we take for granted today was almost entirely missing: oxygen. To modern creatures, that absence would have been fatal. Without oxygen, there was no way for complex animals to breathe, no forest to thrive, no humans to stroll under blue skies. Yet life still managed to exist, clinging to oceans and vents, running on the chemistry available. And then, something extraordinary happened. Life itself began to change the air, altering the course of the planet forever. This was the Great Oxidation event, a turning point in Earth's history, when the atmosphere began to fill with oxygen, setting the stage for complexity to bloom. The key players in this transformation were tiny and unassuming cyanobacteria. These microscopic organisms discovered a way to harness sunlight as an energy source, a process we now call photosynthesis. Unlike earlier forms of photosynthesis, which used other chemicals as raw electron donors, cyanobacteria learned to split water molecules. It was a clever trick, as water was abundant, and it gave them a nearly limitless source of energy. But there was a side effect. Each time they split water to capture energy, they released oxygen gas. To cyanobacteria, oxygen was waste. To Earth, it was revolutionary. At first, the released oxygen didn't build up in the air. Instead, it reacted with other elements, especially iron dissolved in the oceans. The seas rusted, quite literally, forming vast deposits of iron oxide that we still mine today. These ancient banded iron formations, with their striking layers of red and grey, are the geological fingerprints of oxygen's first appearance. For millions of years, oxygen was absorbed into rocks, sediments, and ocean chemistry. Only when these sinks were saturated did oxygen finally begin to accumulate in the atmosphere. Around 2.5 billion years ago, oxygen levels reached a tipping point. For the first time, the atmosphere began to contain significant amounts of it, changing the chemistry of the planet in dramatic ways. Many of the organisms that had thrived in oxygen-free environments found the gas toxic and faced extinction. Whole ecosystems collapsed. replaced by communities that could tolerate or even exploit oxygen. It was a planetary upheaval, sometimes referred to as Earth's first mass extinction, yet it paved the way for something new. The rise of oxygen transformed the planet in both subtle and spectacular fashion. With oxygen available, entirely new forms of metabolism became possible. Cells could extract far more energy from food molecules through aerobic respiration than they ever could through anaerobic pathways. This extra energy opened the door for more complex life forms, allowing cells to grow larger and develop specialized structures. Eventually, it set the stage for multicellular organisms, plants, animals, and everything that breathes today. Oxygen also reshaped Earth's surface and sky. With it, new minerals formed that could not exist in an anoxic world. Rocks changed their chemistry, soils developed differently, and the appearance of red, iron-rich formations became a permanent feature of the landscape. In the upper atmosphere, oxygen molecules bonded into ozone, forming a protective layer that absorbed harmful ultraviolet radiation. This shield allowed organisms to survive closer to the surface and much later to venture onto land without being scorched by unfiltered sunlight. It is difficult to overstate how transformative this was. Before oxygen, Earth was a microbial world, teeming with single-celled life but limited in complexity. After oxygen, the stage was set for the explosion of diversity that would eventually fill oceans with fish, skies with birds, and continents with forests. The Great Oxidation Event is one of the clearest examples of life not only adapting to a planet, but reshaping it on a global scale. The transition was not smooth or immediate. Oxygen levels fluctuated wildly for hundreds of millions of years, rising and falling as life, geology, and climate interacted. Some periods may have seen near-modern levels of oxygen, while others dipped dramatically. These shifts influenced everything from the evolution of organisms to the cycles of glaciation. In fact, some scientists believe that the sudden burst of oxygen may have triggered global cooling events, including possible snowball Earth phases, as methane in the atmosphere was destroyed by the reactive new gas. The balance was delicate, and Earth wobbled through it with difficulty. Eventually, however, oxygen stabilized at levels that allowed complexity to flourish. Around 600 million years ago, oxygen concentrations rose enough to support large multicellular organisms, and soon after came the Cambrian explosion, when diverse life forms appeared in the fossil record in dazzling variety. It was as if oxygen had unlocked the planet's potential, fueling not just survival, but innovation. Even today, oxygen continues to shape the story of life. Every breath taken by animals, every flicker of a flame, every rusting nail is a reminder of the radical shift cyanobacteria set in motion billions of years ago. The air we rely on is not a permanent feature of Earth. It is a product of life's restless creativity. Without those tiny microbes, Earth might still be a quiet world of chemistry, lacking the energy-rich air that makes forests sway and lungs expand. The Great Oxidation Event is a reminder that even the smallest organisms can change a planet. Cyanobacteria had no grand plan, no awareness of what their waste product would accomplish. Yet their steady work altered the atmosphere, the oceans, and the future of every living thing. It shows that life and Earth are inseparable, each shaping the other in a continuous dance. When you pause to breathe deeply, you are participating in that ancient legacy. The oxygen filling your lungs has been recycled countless times, through forests, seas, and the breath of other creatures. It is the same gas that once turned the seas rusty and the skies blue, the same element that made complex life possible. Earth quite literally breathes through its atmosphere, and we are part of that breath. What began as waste from tiny microbes became the atmosphere of a living planet. Oxygen gave Earth its vitality, its resilience, and its diversity. It was the breath of transformation, the moment when the world shifted from a realm of simple chemistry to one capable of extraordinary life. Forests are among the most striking symbols of life on Earth. From the towering giants of the Amazon rainforest to the dark, whispering pines of the boreal north, these ecosystems stretch across continents, breathing with the planet in cycles of growth, decay, and renewal. To stand in a forest is to feel the pulse of Earth itself, a living fabric woven from trunks, leaves, roots, and an unseen network beneath the soil. They're often called the green lungs of the planet, and the metaphor is apt. Forests inhale carbon dioxide, exhale oxygen, and in doing so they sustain the balance of air we depend upon. Rainforests are the most exuberant expression of this green vitality. Found near the equator, they thrive in warm temperatures and heavy rainfall, conditions that allow life to flourish in staggering abundance. A single hectare of rainforest can host hundreds of species of trees, thousands of species of insects, and countless birds, reptiles, and mammals. From the forest floor, sunlight appears filtered through layers of canopy, branches, and vines, each stratum home to its own community. Epiphytes cling to branches high above, orchids bloom in dazzling displays, and troops of monkeys leap between trees. Beneath the surface, the soil may be surprisingly thin and poor, yet the rapid recycling of nutrients by fungi, microbes, and detritivores keeps the system alive. The rainforest wastes nothing. Every fallen leaf is quickly absorbed into the cycle, feeding the relentless growth. At the opposite end of the spectrum lie the boreal forests, also known as taiga, stretching across northern latitudes in Canada, Russia, and Scandinavia. Here, the climate is harsher, winters long and frigid, summers brief but intense. The trees are fewer in species but immense in scale. Endless ranks of conifers, spruce, fir, pine, march across the land, their needle-shaped leaves adapted to withstand cold and snow. Wildlife here is equally hardy. Moose, wolves, and bears stalk through shadowed clearings, while migratory birds return each summer to breed in the fleeting warmth. The boreal forest stores vast amounts of carbon, both in its trees and in the deep layers of peat that lie beneath. These peatlands act like vaults, locking away carbon for thousands of years. In this way, boreal forests are not only lungs but also memory banks, preserving the breath of ages. Between these extremes are temperate forests found in milder regions across Europe, North America, and Asia. They boast a colourful rhythm of seasons, with fresh green in spring, dense shade in summer, fiery reds and golds in autumn, and stark silhouettes in winter. Deciduous trees shed their leaves to survive cold months, creating rich blankets of litter that nourish the soil below. These forests have long been intertwined with human history, providing timber, game, and inspiration for art and myth. They remind us that forests are not just ecological systems, but also cultural landscapes, shaping the way societies grow and imagine the world. At the heart of every forest lies photosynthesis, the quiet process that makes Earth breathe. In green leaves, chlorophyll captures sunlight and uses it to turn carbon dioxide and water into sugar and oxygen. This simple chemical reaction is the foundation of nearly all food chains. Plants store the sugars as energy, animals eat the plants, and predators eat the animals. The oxygen released is taken up by creatures like us, fueling the respiration that powers muscles, thoughts, and lives. In this way, forests act as global lungs, exchanging gases with the atmosphere in a steady rhythm that sustains both themselves and the wider biosphere. This planetary respiration is not static but pulses with cycles. During the growing season, forests across the northern hemisphere draw in huge amounts of carbon dioxide, enough that global levels in the atmosphere actually dip. In autumn and winter, when leaves fall and decay, carbon is released back into the air and levels rise again. This seasonal breathing can be detected in precise measurements, a heartbeat of the planet visible in graphs of carbon dioxide concentration. It is a reminder that forests are not passive scenery, but active participants in Earth's chemistry. Forests also influence climate in ways that extend far beyond their borders. The Amazon, for example, produces enormous amounts of water vapour through transpiration, the release of moisture from leaves. This vapour rises into the atmosphere, forming clouds that eventually fall as rain, much of it within the forest itself. In effect, the rainforest creates its own weather, recycling water to sustain its lush growth. In boreal forests, the dark canopy absorbs sunlight, warming the region, while the snow-covered clearings reflect it, cooling the landscape. These interactions influence temperature, precipitation, and even wind patterns on a continental scale. Beneath the forest floor lies another world, one that's easy to overlook but essential to the whole system. Roots, fungi, and microbes form intricate partnerships that keep nutrients cycling. Mycorrhizal fungi, for example, wrap themselves around roots, extending their reach and helping plants absorb water and minerals. In exchange, the fungi receive sugars produced by photosynthesis. This mutualism links trees together, sometimes even across species, creating networks that allow resources to flow where they are most needed. A mature tree may feed seedlings in its shade, while ailing trees may pass their remaining energy to healthier neighbours. Forests are not just collections of individual plants, but communities bound by cooperation. The importance of forests to human life is hard to overstate. They regulate climate, provide clean water, prevent erosion, and house untold biodiversity. They supply timber for shelter, fuel for warmth, and countless medicines derived from their plants. Culturally, they have long been places of refuge, mystery, and transformation, from the sacred groves of ancient Greece to the enchanted woods of fairy tales. Forests are woven into our imagination as deeply as they are into our survival. Yet they are also vulnerable. Deforestation, driven by agriculture, logging, and urban expansion, removes vast areas of forest each year. When forests vanish, the carbon they store is released, biodiversity is lost, and local climates shift. Rainforests in particular are threatened by clearing and burning, reducing their ability to recycle water and produce rainfall. Boreal forests face pressures from warming temperatures that increase wildfires and pest outbreaks. The loss of forests is not just an ecological concern, but a planetary one, because it disrupts the very respiration of Earth. Despite these challenges, forests remain remarkably resilient. When given time and space, they regenerate, sending shoots from stumps, seedlings from seeds, and roots through soil. Protected areas, reforestation projects, and shifting attitudes about conservation all help in allowing forests to recover. The resilience of trees, their ability to endure storms, droughts, and centuries, reminds us that forests operate on timescales longer than human lives. They are teachers of patience and persistence. To walk among trees is to be reminded of the deep connection between air, water, and life. Each breath we take carries oxygen that once flowed through a leaf, released into the atmosphere by photosynthesis. Each exhale of carbon dioxide is drawn back by plants, completing a cycle that has sustained life for billions of years. Forests do not just provide air, they participate in a planetary dialogue, one in which humans are deeply entangled. Forests, whether rain-soaked, snow-dusted, or seasonally shifting, are more than landscapes. They are organs of the earth, green lungs that help keep the atmosphere balanced and the climate steady. In their growth, decay, and renewal, they embody the rhythms of life itself. When the wind moves through branches, carrying the scent of pine or the humidity of the tropics, it is Earth's breath we are feeling, a gentle exhale of a living planet. At first glance, deserts appear empty, barren stretches of sand and stone where life could hardly cling. The word itself often conjures images of thirst, heat, and desolation. Yet deserts are not voids. They are landscapes of extremes, where survival requires remarkable ingenuity and adaptation. Though water is scarce and conditions harsh, life persists, shaping strategies that reveal just how resilient Earth can be. Arid regions cover nearly 1/3 of the planet's land surface. They come in many forms, from the rolling dunes of the Sahara to the rocky plateaus of the Atacama, from the icy deserts of Antarctica to the scrub-covered expanses of the Australian outback. What unites them is a lack of water. Rainfall is rare and unpredictable, sometimes absent for years at a time. In some deserts, such as the Atacama in Chile, there are places where no measurable rain has fallen for centuries. Yet even here, life endures, waiting patiently for rare moisture or surviving in ways that seem almost impossible. The creatures that live in deserts are masters of adaptation. Camels are perhaps the most famous, their humps storing fat that can be converted into energy and water when food is scarce. Their broad feet prevent them from sinking into sand, and their long eyelashes shield against blowing dust. Smaller animals have equally clever strategies. Kangaroo rats in North America can survive without ever drinking liquid water, deriving all they need from seeds and conserving every drop through specialized kidneys. Insects, lizards, and snakes often burrow into the ground to escape daytime heat, emerging only at night when temperatures are cooler. Life here is not absent but hidden, emerging in brief windows when conditions allow. Plants too have evolved to thrive in deserts. Cacti store water in fleshy stems, protected by spines that deter thirsty animals and reduce water loss. Their shallow roots spread wide, ready to absorb rainfall within minutes of a storm. Other desert plants lie dormant as seeds for years, waiting until the rare rainfall triggers a sudden bloom. These desert flowers can transform a barren landscape into a carpet of colour almost overnight, a fleeting reminder of the vitality stored within apparent emptiness. Deserts also showcase Earth's power to shape landscapes in dramatic ways. Sand dunes are among the most striking features, vast waves of golden grains sculpted by wind. These dunes are never still. They creep forward, advancing meters each year, burying anything in their path. Some can tower hundreds of meters high, ridges shifting and reshaping with each gust of wind. To climb one is to step on something alive in motion, a landform that refuses permanence. Rocky deserts are no less impressive. Towering mesas, jagged canyons, and endless plains speak of erosion and time, where wind and temperature swings slowly sculpt the land. The climate of deserts is marked not only by dryness but by extremes. Temperatures can swing from blistering heat in the day to freezing cold at night. With little moisture to trap heat, the ground radiates warmth into space after sunset, plunging temperatures rapidly. This daily rhythm challenges life to endure not just scarcity but also volatility. Humans who have lived in deserts for millennia, such as the Tuareg of the Sahara or the Bedouin of the Arabian Peninsula, adapted with mobile lifestyles, using animals for transport and relying on intricate knowledge of oases and seasonal cycles. One might imagine deserts as static, unchanging wastelands, but in truth they are dynamic. Shifting winds reshape dunes, flash floods carve canyons, and climate changes push their boundaries in and out. Over geological time, deserts have waxed and waned, expanding during dry periods and shrinking when rainfall returned. The Sahara, often called the world's largest hot desert, has not always been so dry. Thousands of years ago, it was dotted with lakes and grasslands, home to elephants, giraffes, and human settlements. Rock art left behind by early people shows images of swimming figures and abundant wildlife, evidence of a very different world. As the climate shifted, the green Sahara gave way to the desert we know today. This reminder of change underscores the fragile balance that defines Earth's climates. Antarctica, though covered in ice, is also a desert by definition, receiving less precipitation than many of its sandy cousins. Its conditions are harsher still, with cold that plunges well below -50 degrees Celsius and winds that howl across vast empty plains. Yet life persists here too. Penguins huddle on the coasts, lichens cling to bare rock, and microbial communities thrive beneath the ice. Deserts remind us that aridity is not only about heat but about scarcity, and life finds ways to meet the challenge regardless of form. Deserts play a subtle but vital role in Earth systems. Dust lifted from the Sahara, carried high into the atmosphere, drifts across the Atlantic and fertilizes the Amazon rainforest with minerals like phosphorus. In this way, one of the driest places on Earth sustains one of the wettest. Desert winds also influence weather patterns, shaping monsoons and distributing heat. Far from being lifeless wastelands, deserts are integral to the balance of the planet, their barrenness linked to fertility elsewhere. For humans, deserts have always been both a challenge and a source of fascination. They test endurance, pushing travellers to their limits, yet they also inspire awe with their stark beauty. The endless horizon of dunes, the silence broken only by wind, and the night sky unclouded by moisture or light reveal a grandeur found nowhere else. Many cultures see deserts as places of spiritual testing and revelation, where solitude and simplicity strip life to its essentials. In a world often defined by abundance, deserts stand as reminders of resilience. They show that life does not require comfort to thrive. It can endure scarcity, heat, cold, and unpredictability. The adaptations of desert organisms, the shifting of dunes, and the transformations of ancient climates all testify to Earth's ability to reinvent itself. When we think of Earth's living systems, lush forests or fertile plains often come to mind first, but deserts, in their extremes, are equally important. They are proof that life is versatile, that beauty can exist in silence, and that even the harshest places can contribute to the planet's rhythm. To stand in a desert is to witness resilience, to feel the pulse of survival in its purest form. Sand, stone, and silence conceal a hidden vitality, one that echoes the deeper truth of Earth itself, a living planet, adapting, enduring, and always surprising. Ice is more than frozen water. It is memory, a crystalline archive of Earth's climate written layer by layer over millennia. From the towering glaciers that grind their way down mountainsides to the vast polar caps that blanket the poles, ice carries the history of seasons, storms, and ancient atmospheres. To look at ice is to glimpse both the fragility and resilience of the planet, a reminder that Earth's rhythms of freezing and thawing are woven into its identity as a living world. Glaciers are rivers of ice, slow and relentless. They form when snowfall exceeds melting year after year, compressing flakes into dense layers that eventually fuse into solid ice. Under their own weight, glaciers begin to flow, creeping downhill like frozen taffy, carving valleys and scouring rock. Over centuries they sculpt dramatic landscapes, fjords, cirques, and U-shaped valleys that tell of their passage long after the ice retreats. When you stand in a mountain valley with sheer walls and a flat floor, you're standing in the footprint of ice that once moved like a silent bulldozer. At the poles, ice reigns on a colossal scale. Antarctica holds nearly 90% of the world's fresh water, locked into an ice sheet that in places is more than 4 kilometers thick. To the north, the Arctic is crowned by sea ice that waxes and wanes with the seasons, shrinking in summer and spreading in winter. These frozen expanses are not just passive features. They regulate the planet's temperature by reflecting sunlight. This reflective quality, known as albedo, is one reason ice is often called Earth's white memory. The more ice there is, the more sunlight is bounced back into space, keeping the planet cooler. As ice retreats, darker ocean or land absorbs more heat, reinforcing warming in a delicate feedback loop. Permafrost adds another layer to the story. Stretching across Siberia, Alaska, and northern Canada, it is soil that has remained frozen for thousands of years. Within it lie ancient roots, animal remains, and vast stores of carbon locked away in organic matter. When permafrost thaws, it releases greenhouse gases like carbon dioxide and methane, further influencing climate. In this way, ice and frozen ground are not just records of the past, but players in the present. capable of amplifying changes in the atmosphere. The memory held in ice is remarkably detailed. Scientists drill deep cores into glaciers and ice sheets, extracting cylinders that reveal layers like the rings of a tree. Each year's snowfall traps tiny bubbles of air, preserving samples of the atmosphere from long ago. By studying these bubbles, scientists can reconstruct past levels of carbon dioxide, methane, and other gases, tracing climate back hundreds of thousands of years. The record shows cycles of ice ages and interglacials, warm periods and cold snaps, all linked to Earth's orbital patterns and feedback loops. In this frozen library, every flake becomes a letter, every layer a page, chronicling Earth's changing story. These ice archives reveal that climate is anything but static. Over the last million years, Earth has swung repeatedly between glacial and interglacial phases. During the depths of the last ice age, glaciers extended across North America and northern Europe, locking up so much water that sea levels were more than 100 meters lower than today. As the planet warmed, the ice sheets melted, seas rose, and coastlines shifted. Entire land bridges disappeared beneath the waves, isolating populations and reshaping ecosystems. Humanity itself migrated in response to these changes, following retreating ice and newly opened lands. Ice also moves to a shorter rhythm, a seasonal pulse that shapes ecosystems at the poles. In the Arctic, the expansion of sea ice in winter provides a platform for polar bears and seals, while its summer retreat opens waters for whales and migratory birds. In Antarctica, the annual freeze and thaw of sea ice drives the entire food chain, as microscopic algae grow beneath the ice and feed krill, which in turn sustain penguins, seals, and whales. This cycle of waxing and waning ice is a heartbeat of the planet, synchronizing life with temperature and light. Though ice appears still, it is dynamic. Glaciers surge forward, crack, and carve icebergs into the sea. Ice shelves along Antarctica fracture with thunderous sounds, as pieces the size of cities break away and drift. Even the smallest icicle grows and shrinks with changing temperatures, embodying the ceaseless dialogue between freeze and thaw. Ice is always in motion, balancing between solid and liquid, storing water in some times and releasing it in others. For humans, ice has long been both a challenge and a gift. It has shaped landscapes where civilizations rose, redirected rivers that watered crops, and created fertile valleys from glacial deposits. Ice has preserved mammoths in Siberian tundra and ancient artifacts in alpine passes. It has also challenged explorers, who struggled against its cold and unforgiving nature. Yet its role in regulating Earth's climate is perhaps its greatest gift, a silent service we only fully appreciate when we measure its loss. The fragility of ice is a reminder of how connected Earth's systems are. As the atmosphere warms, glaciers retreat at unprecedented rates, sea ice diminishes, and permafrost thaws. These changes are not isolated to the poles. They ripple globally, altering sea levels, weather patterns, and ecosystems. The white memory of the planet is fading in places, rewriting coastlines and reshaping the future. Still, ice endures as a symbol of resilience. It has grown and shrunk many times over Earth's history, retreating during warm periods and returning when conditions cooled. Even when reduced, it never vanishes entirely, holding on in mountain peaks and polar shadows. Its cycles remind us that Earth is dynamic, a planet of shifting balances rather than fixed states. To hold a fragment of ancient ice in your hand is to hold time itself, a piece of atmosphere breathed by creatures long gone. To watch a glacier groan and crack is to witness geology in motion, slow but relentless. To stand before the shimmering expanse of the polar caps is to feel the vastness of Earth's memory, written not in words but in frost and crystal. Ice is not just frozen water. It is the archive of Earth's climate, the mirror of its rhythms, and the reminder that in every freeze and thaw lies the story of a living planet. Mountains rise like the bones of the earth, vast stone giants that dominate horizons and inspire awe, To stand at their base is to feel small, yet also deeply connected to the restless forces beneath the surface. Though they appear eternal, mountains are not fixed monuments. They are living landscapes, born of uplift and worn down by erosion, constantly changing in a cycle that spans millions of years. Their peaks and valleys are more than scenery. They are engines of rivers, cradles of biodiversity, and symbols that have shaped human imagination since the dawn of time. The story of every mountain begins far beneath our feet, where tectonic plates meet and struggle against one another. When plates collide, the crust crumples, folds and thrusts upward, creating ranges that scrape the sky. The Himalayas, still rising today, were born when the Indian plate slammed into Eurasia, lifting rock into peaks more than 8 kilometers high. Elsewhere, volcanoes build mountains by erupting lava and ash, layer upon layer, until they tower above the plains. Even fault lines, where plates grind past one another, can raise mountains through uplift. Each type of range tells a different tale of Earth's restless crust. Once mountains rise, they are immediately shaped by the forces that wear them down. Wind, rain, ice and rivers carve their slopes, carrying sediment away to form valleys and plains below. Glaciers gouge deep U-shaped troughs, while rivers slice sharp V-shaped canyons. Over millions of years, erosion can grind down even the tallest giants, leaving behind plateaus or isolated peaks as reminders of their former grandeur. Mountains are never finished. They are works in progress, sculpted simultaneously by the forces that build them and the forces that tear them apart. Mountains are also fountains of water. Their height forces air to rise, cool and condense, producing rainfall that feeds rivers. The Andes send life-giving waters across South America, while the Himalayas supply the great rivers of Asia, the Ganges, the Indus, the Mekong, the Yangtze. Snow that accumulates on peaks during winter melts in spring, releasing steady flows that sustain valleys and plains far below. Without mountains, many of the world's rivers would falter, and the fertile lands that depend on them would vanish. This role as water towers makes mountains critical for biodiversity. Where moisture falls, life follows, and mountain slopes often host a staggering variety of ecosystems packed into a small area. A climb from base to summit is like walking from the tropics to the Arctic in a single day, each elevation band home to different communities of plants and animals. In the Andes, llamas graze on high-altitude grasses, while orchids thrive in lower cloud forests. In the Himalayas, snow leopards patrol icy ridges, while rhododendrons bloom in alpine meadows. The isolation of mountain valleys has also encouraged unique species to evolve, many found nowhere else on Earth. Human history is deeply entwined with mountains. For early civilizations, they provided shelter, resources, and barriers. Mountains offered stone for tools and building, forests for timber, and ores for metals. They also shaped cultures by separating groups, fostering unique traditions on either side of a range. Yet mountains were never just obstacles or resources. They have always inspired reverence. Many traditions saw them as sacred, dwelling places of gods or ancestors. Mount Olympus in Greece was the throne of Zeus. Mount Fuji in Japan is still revered as a symbol of beauty and spirituality. In the Andes, mountains known as apas are honoured as living spirits. Their sheer presence has always stirred awe and wonder. The challenge of climbing mountains has also drawn humans for centuries. To ascend is to push against limits, to stand where few have stood before. Expeditions to peaks like Everest or K2 are modern echoes of an ancient impulse. To look up at a summit and feel compelled to reach it. Yet even for those who never climb, mountains hold a special power. They appear in art, literature and music as symbols of endurance, majesty and mystery. They remind us of both the strength and fragility of Earth, rising high yet worn by every storm. Despite their grandeur, mountains are vulnerable. Climate change is altering snowpacks and glaciers, reducing the water supplies that billions of people rely on downstream. Mining and deforestation scar their slopes, disrupting ecosystems and eroding soil. Tourism, while often beneficial, can place strain on fragile alpine environments. Protecting mountains is not only about conserving scenery, it is about safeguarding the lifeblood of rivers, the homes of unique species, and the cultural identities tied to their presence. Mountains also serve as natural laboratories. By studying their rocks, scientists uncover the history of Earth's interior and the story of plate tectonics. Fossils found high in the Alps or Himalayas reveal that these peaks were once seabeds, lifted to the sky by tectonic collisions. Glacial deposits show the rhythms of ice ages, while tree lines mark shifts in climate over centuries. Every ridge and valley is a record of deep time, waiting to be read. When you look at a mountain, you are seeing more than stone. You are witnessing a process, a dialogue between the earth pushing upward and the elements pulling downward. The peaks may appear timeless, but they are moving, rising millimetre by millimetre, even as rain and wind carry them away grain by grain. They are reminders that stability is an illusion, and that change is the only constant, even in stone. To walk among mountains is to step into a realm where Earth speaks in grand scale. The thin air, the sweeping views, the silence broken only by wind or water, all remind us of the planet's power and patience. Mountains are stone giants in motion, sculptors of rivers, keepers of biodiversity, and mirrors of human awe. Their grandeur humbles us, yet their vulnerability calls for care. They endure, but they also transform, just as we do, standing as symbols of Earth's living, breathing nature. Rivers are Earth's restless artists, carving valleys, shaping plains, and chiseling canyons with patience measured in millennia. From trickling streams on mountain slopes to great torrents like the Amazon or the Nile, rivers never cease their work. Each drop of water carries with it grains of sand, bits of soil, and fragments of rock, slowly sculpting the face of the planet. In time, they cut deep gorges, spread wide deltas, and leave behind fertile valleys that nurture both ecosystems and civilizations. To follow a river's course is to trace a pathway of life itself. At their birth, rivers are often small and energetic, tumbling down mountainsides where snow melts and glaciers retreat. These youthful streams carve sharp valleys, leaping over cliffs in waterfalls and rushing through narrow gorges. As they descend, they gather strength, joined by tributaries until they become wide, meandering giants flowing across plains. Over long ages, rivers smooth landscapes, eroding mountains and carrying sediment toward the sea. The Grand Canyon in Arizona is a testament to this power, a vast scar etched by the Colorado River over millions of years. With nothing more than persistence and flow, rivers sculpt landscapes on a scale that no human tool could match. But rivers are more than geologic artists. They are lifelines, bringing fertility to lands that would otherwise be barren. Floodwaters spread nutrient-rich silt across valleys, replenishing soils year after year. The Nile's annual flooding sustained ancient Egypt for millennia, creating fields of grain along the desert's edge. In Mesopotamia, the Tigris and Euphrates rivers made possible some of the earliest cities and the rise of written history. The Indus River supported thriving societies on the Indian subcontinent, while the Yellow River nourished dynasties in China. Again and again, human civilization took root, not in dry uplands, but along waterways that offered food, transport, and connection. Rivers serve as natural highways, long before roads or railways existed. Canoes, barges, and ships have carried people, goods, and ideas along their courses for thousands of years. The Mississippi tied together the heart of North America, just as the Danube linked Europe. The Yangtze carried China's commerce, and the Amazon remains a vital artery of South America. Along these waterways, cultures mingled, markets grew, and societies flourished. Even in modern times, rivers remain essential for trade, irrigation, and power, their flow harnessed by dams and canals to fuel industries and light cities. Beyond their practical roles, rivers nurture ecosystems of astonishing richness. Their banks provide habitats where forests thrive, wetlands filter water, and fish spawn in abundance. Birds migrate along rivers as though following invisible roads, pausing to feed and rest. Crocodiles bask on warm shores, while otters slip through eddies. The shifting floodplains of rivers are among the most productive landscapes on Earth, supporting countless species of plants and animals. To watch a river is to see constant activity, from the ripple of fish breaking the surface to the flight of insects skimming over the water. The dynamics of rivers are marked by constant change. Meanders swing wide across plains, looping back until they nearly touch, then cutting through to create oxbow lakes. Floods reshape banks, uprooting trees and depositing fresh soil. In their deltas, rivers split into braided channels, spreading into wetlands that are nurseries for life. These deltas, like those of the Ganges, the Mekong, or the Mississippi, are vast mosaics of water and land, feeding millions of people while sheltering unique ecosystems. Yet they are fragile too, vulnerable to rising seas, upstream dams, and changes in sediment supply. For all their gifts, rivers also remind us of their power. Floods can devastate cities, sweeping away homes and farmland. They can shift course entirely, abandoning one channel for another, leaving behind ghost towns where once there were thriving ports. Yet even in their destruction, rivers remain essential. They cleanse, renew, and transform, reminding humanity that control is an illusion and that living alongside a river means respecting its cycles. Culturally, rivers have always inspired reverence. They're woven into myth and legend, often seen as sacred or divine. The Ganges is honoured in India as a goddess, its waters believed to cleanse and purify. In ancient Greece, rivers were personified as gods, guardians of valleys and plains. Poets and storytellers across ages have looked to rivers as symbols of time, continuity and change. A river flows ever onward, never quite the same from one moment to the next, yet always connected from source to sea. The resilience of rivers is matched by their vulnerability. Pollution, overuse, and damming disrupt their natural flow. In some places, rivers no longer reach the ocean at all, their waters drained by irrigation and diversion. The Aral Sea, once fed by the Amu Darya and Syr Darya rivers, has shrunk to a fraction of its size, a stark example of how human choices can alter entire landscapes. Restoring rivers, allowing them to flow more freely, and protecting their ecosystems are challenges for the future, because they are more than resources. They are living systems upon which we all depend. To think of rivers as arteries is more than a metaphor. They carry not only water but also nutrients, sediments, and life itself, linking mountains to oceans and ecosystems to one another. They are Earth's circulatory system, pulsing through landscapes with a rhythm that sustains both the smallest insect and the largest civilization. When they flow strong and healthy, the planet flourishes. When they are choked or diminished, the consequences ripple far and wide. To sit on the bank of a river is to watch the passage of time. Leaves drift, fish rise, clouds reflect on the surface, yet beneath that calm exterior is power, patient but unyielding. The same flow that soothes the senses is also the force that carved canyons, built valleys, and nourished societies. Rivers remind us that change can be both gentle and immense, both nurturing and overwhelming. They are the sculptors of landscapes, the lifeblood of civilizations, and the living arteries of Earth. From mountain springs to ocean deltas, rivers are constant yet ever-changing, shaping the world in ways both visible and hidden. To follow their course is to follow the story of Earth itself, written not in stone or sky but in water that never ceases to move. Everywhere you look on Earth, life is woven into patterns. A blade of grass sways in a meadow, but it is not alone. Insects crawl upon it, grazers nibble it, and the soil beneath holds roots and fungi that sustain it. A wetland hums with the calls of birds while reeds filter water and frogs leap between pools. In the frozen tundra, lichens cling to rocks, and caribou trek across icy plains. Each of these places is a biome, distinct in its climate and inhabitants, yet none of them stands apart. They are threads in a single web of ecosystems, connected in ways both obvious and subtle, forming a planetary network that makes Earth more than a collection of landscapes. It makes Earth a living system. Grasslands are some of the most expansive of these biomes, covering vast stretches of continents where rainfall is enough to sustain grasses but too little to support dense forests. The Serengeti in Africa, the prairies of North America, and the steppes of Eurasia are examples of these rolling seas of green. Grasslands pulse with migrations, wildebeest thundering across the plains, bison grazing in herds, or saiga antelope moving with the seasons. Beneath the surface, grasses send down deep roots that stabilize the soil and hold carbon. These roots endure fire and drought, making grasslands resilient against change. Yet they are also fragile when disrupted, and overgrazing or conversion to farmland can unravel their balance. Wetlands may not appear as vast, but their importance is immense. They are the in-between zones where water meets land, places of marshes, swamps and deltas. Here, productivity is astonishing. Plants like reeds and cattails filter sediments, purify water and provide nurseries for fish. Birds congregate in flocks to feed and nest, while amphibians thrive in the damp margins. Wetlands act as sponges, absorbing floodwaters during heavy rains and releasing them slowly during dry periods. They are among the most effective ecosystems for storing carbon, capturing greenhouse gases in soils rich with organic matter. Yet despite their value, wetlands have often been drained or filled, treated as wastelands rather than lifelines. Only in recent decades has their true worth been recognised. Tundra, by contrast, is a land of scarcity and extremes. Found in the far north and on high mountains, it endures cold, wind, and a short growing season. Trees cannot survive, so mosses, lichens, and hardy shrubs dominate. Yet life finds ways to endure. Caribou and reindeer roam in herds, feeding on lichens beneath the snow. Arctic foxes and snowy owls patrol the open expanses. In summer, when the sun lingers above the horizon for weeks, the tundra bursts into sudden activity. Flowers bloom, insects swarm, and migratory birds arrive to nest. Beneath it all lies permafrost, frozen soil that locks away carbon and shapes the landscape. When it thaws, entire ecosystems shift, releasing gases and altering the delicate balance of climate. Though each biome has its own character, they are linked by flows of energy, matter, and life. Rivers connect mountains to wetlands, carrying nutrients and sediments that sustain faraway deltas. Migratory animals traverse continents, linking ecosystems thousands of kilometers apart. A bird hatched in Arctic tundra may feed in temperate wetlands before spending the winter in tropical grasslands, tying together distant worlds with its journey. Even winds and currents play a role, transporting dust, seeds, and spores across oceans and continents. The Sahara's dust feeds the Amazon soils, a reminder that deserts and rainforests, though worlds apart, are part of one global system. Within each ecosystem, symbiotic relationships form the fine threads of connection. Mutualism, where species benefit one another, is common. Bees pollinate flowers while gathering nectar. Clownfish shelter among the stinging tentacles of sea anemones, gaining protection while defending their host from intruders. In forests, mycorrhizal fungi link trees underground, sharing nutrients and signals. Parasitism and competition also play roles, keeping populations in check and driving adaptation. Each species, no matter how small, is part of a wider network, and when one disappears, others are affected. The web of ecosystems is strong but also sensitive. like a net where the loss of one knot loosens many others. The idea of Earth as a single system emerges clearly when these connections are seen together. Scientists call it the biosphere, the sum of all ecosystems interacting with the atmosphere, the hydrosphere, and the geosphere. Life does not simply live on Earth, it actively shapes it. Forests draw carbon from the air, influencing climate. Oceans absorb and release gases, regulating temperature. Microbes in soil fix nitrogen, making it available for plants, which in turn feed animals. Each cycle is intertwined, forming feedback loops that maintain balance. In this sense, Earth behaves almost like an organism, self-regulating through countless small interactions. Human history has been profoundly shaped by these ecosystems. Civilizations grew in fertile river valleys, thrived on grasslands rich in game, and relied on wetlands for food and protection. Even today, cities are built within this web, dependent on resources that flow from ecosystems far away. A meal on a plate may involve grains from grasslands, fish from wetlands, and fruit pollinated by insects in distant forests. Modern economies are stitched directly into the biosphere's fabric, whether we acknowledge it or not. Yet the web is delicate. Deforestation in rainforests alters rainfall patterns far beyond their borders. The draining of wetlands increases flooding downstream. The thawing of tundra releases carbon that influences global temperatures. Each biome is local, but its effects are global. Recognizing Earth as a single system means recognizing that no part can be treated in isolation. A change in one thread tugs at the entire web. There is beauty in this interdependence. It means that life is not fragmented, but unified, a vast conversation conducted in water, soil, air, and genes. To walk through a meadow, paddle in a swamp, or trek across tundra is to step into strands of a network that extends across the planet. Even the air we breathe carries the signatures of distant ecosystems. Oxygen exhaled by forests, moisture lifted from oceans, carbon absorbed and released by soils. The resilience of ecosystems is matched by their vulnerability. They recover from storms, fires, and floods, yet they can be undone by prolonged pressure. Protecting them requires not only preserving individual habitats, but also respecting the connections between them. Grasslands, wetlands, and tundra are not isolated theatres, but parts of a single performance, each contributing to the harmony of Earth's living system. To see Earth as a web of ecosystems is to see the planet as more than geography. It is to recognise the invisible threads binding every biome, every species, and every process into a whole. Life thrives not because of isolation, but because of connection, and in those connections lies the secret of a planet that endures. Earth is not a patchwork of habitats. It is a living, breathing unity, a symphony of ecosystems playing in concert. Life on Earth has never enjoyed a smooth and steady path. Again and again, the planet has been jolted by catastrophes so severe that entire worlds of creatures vanished, landscapes transformed, and climates rewrote themselves. To call these events destructive is accurate yet incomplete. Each catastrophe carried within it the seeds of renewal, clearing the stage for new players and new possibilities. Earth's history is a testament to resilience, where endings become beginnings, and upheaval sparks creativity in the long arc of evolution. One of the most famous catastrophes arrived from the sky. About 66 million years ago, a massive asteroid, more than 10 kilometers wide, struck near what is now the Yucatan Peninsula. The impact unleashed energy greater than billions of nuclear bombs, throwing molten rock and dust into the atmosphere. Fires swept across continents, earthquakes rippled globally, and tsunamis surged outward from the impact site. Perhaps most devastating was the aftermath. Fine particles lofted high into the stratosphere blocked sunlight for months or years, collapsing food chains and plunging the planet into darkness. Dinosaurs, which had dominated Earth for over 100 million years, could not withstand the combined shock of fire and famine. Yet in their absence, mammals, once small and marginal, began to flourish, eventually giving rise to primates and humans. Out of disaster came opportunity. Meteor strikes are dramatic, but Earth's own interior has delivered catastrophes just as devastating. Volcanic eruptions, on scales far beyond anything witnessed in recorded history, have periodically reshaped the planet. The Siberian Trap's eruption about 252 million years ago poured out lava across millions of square kilometres, releasing enormous amounts of carbon dioxide and sulfur gases. The sky filled with ash, acid rain fell, and the oceans grew toxic. This event, known as the Great Dying, wiped out over 90% of marine species and 70% of land species. It was the most severe mass extinction in Earth's history, a near reset of the biosphere, and yet from that collapse came the rise of new groups, including the ancestors of dinosaurs, who would go on to dominate the next era. Volcanic winters have also played a role on shorter timescales. When the Indonesian volcano Mount Tambora erupted in 1815, the explosion was so powerful that it darkened skies around the world. The following year became known as the Year Without a Summer, with crop failures and famines spreading across Europe and North America. If a single eruption could create such turmoil, it is easy to imagine the effects of larger prolonged events in prehistory. These winters chilled the climate, stressed ecosystems, and contributed to extinctions, yet they also forced adaptation and migration. Life had to adjust, finding niches in new conditions. Not all catastrophes came suddenly. Some unfolded slowly but relentlessly, altering the planet's balance until ecosystems faltered. Changes in ocean chemistry, shifts in atmospheric gases, or gradual climate swings all played their part. About 55 million years ago, a rapid release of carbon into the atmosphere triggered the Paleocene-Eocene thermal maximum, a global warming event that lasted for hundreds of thousands of years. Temperatures rose by 5 to 8 degrees Celsius, oceans became acidic, and many species struggled to cope. Yet the event also spurred migrations and innovations, with early mammals diversifying and spreading across continents. Evolutionary creativity often blooms in the aftermath of disruption. Mass extinctions punctuate Earth's history like chapters in a long book. The Ordovician extinction over 400 million years ago, likely driven by global cooling and glaciation, cleared the seas of many early marine creatures. The Devonian extinction, unfolding over millions of years, reshaped ocean life again, making room for the ancestors of modern fish. The Permian extinction nearly erased life altogether, but recovery led to the rise of reptiles and eventually dinosaurs. The Cretaceous extinction ended the dinosaurs' reign, but it opened the door for mammals and birds. Each time, catastrophe was followed by diversification, a pattern of collapse and renewal that underscores the resilience of life on Earth. To understand why these destructive events can also be creative, it helps to see ecosystems as dynamic. When dominant groups are wiped out, opportunities open for others. After the dinosaurs vanished, mammals filled ecological roles once occupied by giants, evolving into forms as small as mice and as large as whales. After reefs collapsed in mass extinctions, new builders emerged to create entirely different ecosystems. Catastrophes reset the competition, allowing new strategies to flourish. Evolution, in this sense, thrives on disturbance. This does not mean that catastrophes are gentle. For the organisms caught in them, they are brutal and final. Entire lineages vanish, leaving no descendants. Yet from the planetary perspective, these events are part of the story of resilience. Life adapts, changes, and rebuilds, often in surprising ways. What seems like an end is more often a transition, one that reshapes the direction of evolution. Humans, too, live in the shadow of catastrophe. While our species has not yet endured a global extinction event, history shows how even smaller disruptions have shaped us. Ice ages forced migrations, volcanic eruptions challenged survival, and diseases swept across continents. Each trial tested resilience and ingenuity. Today, with the ability to alter the climate and landscapes on a global scale, humans find themselves in the position of both victim and agent of catastrophe. The choices we make could determine whether we tip Earth systems into crises of our own making, or whether we learn from the resilience written into the planet's past. What is striking is not just the destructiveness of these events, but Earth's ability to recover. After the Great Dying, reefs rebuilt, forests regrew, and new creatures evolved. After the asteroid strike, mammals, birds, and flowering plants spread into niches once dominated by reptiles. Even after smaller catastrophes, like volcanic winters or regional collapses, life found ways to return. Earth has an astonishing capacity for renewal, though it operates on timescales far longer than human lifetimes. To reflect on these catastrophes is to recognize both the fragility and endurance of life. Fragile, because entire worlds of species can vanish in an instant. Enduring, because from the ashes of loss, life reimagines itself again and again. Earth is not a static museum of organisms, but a living stage of constant rehearsal, where catastrophes clear the set for new performances. Next time you hear of an asteroid streaking across the sky, or a volcano rumbling beneath its peak, consider that such forces, terrifying as they seem, are part of the same system that made life diverse and resilient. The catastrophes that shaped life remind us that Earth's story is not one of uninterrupted calm, but of upheaval and recovery. Out of fire, ice, and impacts, life has found ways to flourish, and it is this resilience that defines our living planet. Earth does not move through the cosmos alone. Since its earliest days, it has been accompanied by a companion, a silent partner in its journey around the sun, the moon. To the casual eye, the moon is simply a pale disk that waxes and wanes across the sky. Yet its presence has shaped Earth in profound ways. Without the moon, the tides would be weaker, the planet's axis less stable, and the rhythm of life itself very different. It is a cosmic dance, subtle and enduring, that has helped make Earth the habitable world we know. The story begins with a colossal impact. Billions of years ago, not long after Earth formed, a Mars-sized body is thought to have collided with our planet. The violence of this event flung molten rock into orbit, which over time coalesced into the moon. It was born of fire and chaos, yet it became a stabilizing force. This unlikely origin gave Earth more than just a satellite. It gave it balance. One of the moon's most visible influences is the tides. As the moon's gravity pulls on Earth, it draws the oceans into bulges that rise and fall as the planet rotates. Twice each day, shores around the world feel the tug of the moon as water surges in and retreats again. These tides may seem like a simple feature of coastal life, but they have had far-reaching effects. In the early history of life, tides created shifting zones between land and sea, places of challenge and opportunity where organisms adapted to both wet and dry conditions. These intertidal zones may have been the stepping stones that encouraged life to venture onto land. Even now, tides nourish estuaries, stir nutrients in the oceans, and guide the migrations of countless species. The moon also acts as a stabilizer for Earth's axis. Our planet tilts at about 23.5 degrees relative to its orbit around the sun, and it is this tilt that creates the seasons. Without the moon, gravitational tugs from other planets, particularly Jupiter, might cause Earth's tilt to wobble chaotically over time. The result would be unpredictable and extreme climate shifts, making it far harder for stable ecosystems to take root. Instead, the moon's steady pull damps these variations, keeping Earth's tilt relatively constant. Thanks to this balance, winters and summers follow a dependable rhythm, allowing life to adapt and flourish in stable cycles. This stabilizing influence extends beyond climate into the psychology of life itself. The moon's monthly cycle has been a timekeeper for cultures throughout history, marking calendars and guiding agriculture. Its phases have inspired myths, poetry, and ritual, connecting human imagination to the cosmos. The full moon, lighting a night sky, has been a constant across ages, a companion to travellers and a muse for storytellers. In this sense, the moon is more than a physical partner. It is also a cultural one, shaping the way humans see their place in the universe. The gravitational bond between Earth and the moon has other consequences too. Over time, the moon has gradually slowed Earth's rotation through tidal friction. Billions of years ago, a day on Earth may have lasted only 6 hours. As tides pulled on the oceans, energy was transferred, slowing the spin of Earth and causing the moon to drift farther away. Even now, the moon is receding at a rate of about 4 centimeters per year. It is a slow farewell, one that will eventually change the length of Earth's days and the size of its tides. Yet in the grand timescale of billions of years, this gradual drift has given Earth longer, more temperate days, shaping the pace of life. Life on Earth has adapted to the moon's rhythm in ways both subtle and profound. Certain species, from corals to fish, time their reproductive cycles to the lunar calendar, ensuring that spawning coincides with particular tides or phases of the moon. Sea turtles return to beaches under moonlight to lay their eggs, guided by cycles as old as their lineage. Even human sleep and behaviour show faint traces of lunar influence, a reminder that our biology is still tuned to the dance of our planet and its satellite. If Earth had no moon, the story of life might have been entirely different. Tides would be weaker, reducing the mixing of coastal waters and the opportunities for early organisms to adapt between land and sea. Earth's tilt would wobble more drastically, leading to unpredictable climates that could stifle the long-term evolution of complex ecosystems. Days would have been shorter for much of Earth's history, with faster rotation creating more violent winds and storms. The moon's presence smoothed these extremes, offering a stage more suited to the gradual unfolding of life. The moon's silence is part of its charm. Unlike Earth, it has no atmosphere to speak of, no weather, no oceans. Its craters preserve scars of ancient impacts, a frozen record of a violent solar system long past. And yet, despite its stillness, the moon has been Earth's most constant companion, circling faithfully, its pull always present, its phases marking time. From the perspective of space, the two form a binary system, orbiting around a common centre of gravity. It is not Earth alone, but Earth and Moon together that describe this elegant dance. For humans, the moon has always been a source of wonder. Its face, visible even to the naked eye, connects every culture across time. The same moon that guided ancient sailors still rises over modern cities. The Apollo missions of the 20th century extended this connection, allowing humans to set foot on its surface and look back at Earth hanging in the sky. That view, the blue marble framed by the desolate lunar horizon, remains one of the most profound reminders of Earth's uniqueness. The moon gave us perspective, showing our planet not as an endless expanse, but as a fragile sphere in the cosmos. As Earth continues its journey around the sun, the moon remains its partner, shaping tides, stabilizing seasons, and influencing the length of our days. It is a relationship measured not in years or centuries, but in billions of years. A quiet companionship that has made life possible in ways both obvious and hidden. To look at the moon is to see more than a satellite. It is to see the silent partner in Earth's rhythm, the steady presence that has guided oceans, balanced climates, and inspired minds. Earth without the moon would be a different planet, perhaps less stable, perhaps less alive. Together they form a duet, a cosmic dance written in gravity and time, still unfolding beneath the stars. Among the planets of the solar system, Earth holds a privileged seat in a grand performance, a symphony of orbits, light, and gravity. It is not the largest planet, nor the smallest. It is not the closest to the sun nor the farthest, yet somehow it is just right. Positioned in what astronomers call the habitable zone, Earth circles the sun at a distance where liquid water can exist, where warmth balances against cold, and where life as we know it has had billions of years to unfold. The planet's story is not only one of geology and biology, but also of cosmic placement, a harmony of luck and law that allows it to thrive in the solar symphony. The habitable zone is sometimes nicknamed the Goldilocks zone, where conditions are neither too hot nor too cold but just right for liquid water. Venus orbits closer to the Sun and has been baked into a furnace under a blanket of carbon dioxide, with surface temperatures hot enough to melt lead. Mars lies farther out, its thin atmosphere unable to hold heat, leaving its surface frozen and dry. Earth, in between, enjoys a balance. Here, oceans remain liquid, ice caps endure but do not consume the planet, and atmospheric gases sustain a climate suitable for life. This placement is not a narrow miracle, but a delicate balance of distance, atmosphere, and planetary dynamics that together create a world where rivers flow and forests grow. The Sun, too, is a key part of this story. It is a stable star, luminous but not erratic, burning hydrogen in a long, steady main sequence phase that has lasted for over 4 billion years. Its energy reaches Earth in a predictable rhythm, warming land, sea, and air. Yet the Sun is not perfectly constant. It pulses with cycles, most famously the 11-year cycle of sunspots, where magnetic activity waxes and wanes. During active periods, solar storms hurl charged particles toward Earth, stirring auroras at the poles and occasionally disrupting satellites and power grids. Despite these fluctuations, the Sun's output remains within a range that allows life to persist. It is both steady conductor and dramatic soloist, guiding the tempo of Earth's climate and rhythms. Earth does not simply receive sunlight passively, it interacts with it. The tilt of the planet's axis divides sunlight unevenly across seasons, creating winters, summers, and the migration of ecosystems. Clouds and ice reflect some sunlight, while forests and oceans absorb it. Green plants use sunlight to power photosynthesis, transforming energy into food and releasing oxygen. In this way, Earth's biosphere captures starlight and translates it into the energy of living systems. The sun's light becomes the beating of a heart, the unfolding of leaves, the swimming of fish, and the breath of animals. The symphony of the solar system is not only orbital but biological. Cosmic luck played its part in shaping this harmony. Earth's orbit is nearly circular, keeping its distance from the Sun relatively constant. A more elongated orbit could have produced harsh swings between scorching heat and icy cold, destabilizing climates. The giant planets, particularly Jupiter, also help by deflecting many incoming comets and asteroids that might otherwise bombard Earth more frequently. The size of Earth itself matters too, large enough to hold onto an atmosphere, small enough to avoid crushing gravity or excessive internal heat. Each factor is like an instrument in the orchestra, contributing to the melody of habitability. Yet natural laws underpin this luck. Gravity, thermodynamics, and orbital mechanics set the stage for what is possible. The same laws that keep Earth in orbit also govern the tides, the circulation of air, and the energy captured by plants. The balance between cosmic chance and physical necessity is what makes Earth remarkable. It is not that the planet was destined to be alive, but rather that it fit into a set of conditions where life could arise and persist. The solar symphony provides the music, and Earth has learned to dance to it. Life itself has added new notes to the performance. By altering the composition of the atmosphere, organisms have changed how Earth interacts with sunlight. Cyanobacteria filled the air with oxygen, creating an ozone layer that shielded life from ultraviolet rays. Plants spread across continents, darkening land surfaces and altering how much heat was absorbed. Humans, in more recent times, have altered the climate by burning fossil fuels, increasing greenhouse gases and changing the balance of heat retained. The solar symphony is not played only by stars and planets. Life itself is part of the orchestra, feeding back into the rhythms that sustain it. The solar system as a whole provides both harmony and challenge. Earth shares its neighbourhood with asteroids, comets, and other planets, whose gravitational nudges can alter orbits over vast timescales. From time to time, Earth has been struck by celestial visitors, with consequences ranging from local devastation to global catastrophe. Yet even these disruptions are part of the symphony, moments of percussion that reset the melody of life. The moon, born from a colossal impact, now steadies Earth's tilt and draws tides, adding its own rhythm to the score. The solar system is not a quiet concert hall, but a stage of interplay where stability and disruption mingle. From Earth's perspective, the sun is the centre of everything. It dictates the length of days and years, the cycles of growth and rest. But in the larger symphony of the galaxy, even the sun is only one instrument circling the Milky Way every 200 million years. The stage grows larger, the music deeper. Earth's habitability is not only about its placement in the solar system, but also about the stability of the galaxy around it, where supernovae and cosmic radiation could disrupt the score. Once again, luck and law entwine, and Earth benefits from both. The wonder of Earth's position is not that it is perfect, but that it is balanced. It lies close enough to the sun to stay warm, yet far enough to avoid becoming a furnace. Its atmosphere holds heat gently, yet not so tightly as to smother. Its orbit is stable, yet dynamic enough to create seasons. In this balance, the solar symphony becomes more than physics. It becomes the setting for oceans, forests, deserts, and cities. To sit under the sun and feel its warmth is to experience directly the music of this symphony. The light on skin, the shimmer of water, the shadows cast by trees, all are expressions of Earth's position and its dialogue with the sun. When night falls and the moon rises, the harmony continues, a duet between planet and satellite, guided always by the sun's enduring presence. Earth's place in the solar symphony is a reminder that life is not inevitable but possible, nurtured by balance and sustained by resilience. The melody of orbit, sunlight, atmosphere, and biology has played for billions of years, and for now it continues. To listen closely is to hear not only the harmony of chance and law, but also the quiet truth that we are part of this music, shaped by it, and sustained within it. For most of Earth's history, change has come from slow geological shifts, from ice ages and volcanic eruptions, from drifting continents and the long sweep of evolution. Yet in the blink of geological time, a new kind of force appeared, one that walks on two legs, uses tools, and dreams in symbols. Humans are more than just inhabitants of Earth. They have become shapers of it. Through fire, farming, cities, and machines, humans have altered the planet on a scale that rivals rivers, glaciers, and tectonic plates. We are, for better and for worse, a force of nature. Our journey as ecosystem engineers began modestly. Early humans lived within the rhythms of their environments, gathering plants and hunting animals. Yet even then, small sparks of influence can be traced. Controlled fire was one of the first great tools used to clear grasslands, drive game, and alter landscapes. Fire changed plant communities, encouraged certain species to grow, and kept others in check. What began as survival soon became engineering. Humans learned they could shape ecosystems to suit their needs. The most dramatic shift came with agriculture. Around 10,000 years ago, in river valleys and fertile plains, humans began to cultivate plants and domesticate animals. Instead of wandering after food, they coaxed food to grow where they settled. Wheat, rice, maize, and potatoes became foundations of societies, while sheep, cattle, and goats provided meat, milk, and fibre. Farming turned forests into fields and wetlands into paddies. Irrigation systems diverted rivers, terraces reshaped hillsides, and landscapes once ruled by wild rhythms became ordered mosaics of human intention. With agriculture came surpluses, and with surpluses came cities. Settlements grew into centres of trade, culture, and governance. Cities concentrated people and resources, altering local environments in profound ways. Forests were cut to build homes and ships, quarries supplied stone for monuments, and air was filled with smoke from hearths and kilns. Rivers were redirected to supply growing populations, and walls and roads etched permanent lines into the land. Cities became hubs where human influence radiated outward, their needs reshaping distant forests, mines, and farmlands. The industrial era magnified this influence beyond anything seen before. Coal, oil, and natural gas unlocked vast stores of energy, fueling machines that multiplied human labour many times over. Steam engines powered railroads, factories, and ships. Electricity lit homes and powered industries. Automobiles and airplanes shrank distances, while massive factories produced goods on a scale unimaginable in earlier times. With this expansion came both marvels and costs. Skyscrapers rose, bridges spanned rivers, and communication leapt across oceans. At the same time, smoke-filled skies, rivers ran with waste, and forests fell at accelerating rates. Through industry, humans became global in their reach. A single city's appetite for timber could drive logging in distant continents. The demand for fuel transformed entire regions into mines and oil fields. Crops grown in one hemisphere fed populations in another, transported by ships and planes. For the first time, the entire planet became a connected system of human exchange, bound together by trade, technology, and consumption. This scale of our influence grew so vast that scientists now debate whether Earth has entered a new geological epoch, the Anthropocene, the age of humans. Yet our role is not only as disruptors, humans are also caretakers. Throughout history, people have cultivated not just crops but gardens, forests, and landscapes with an eye for balance. Indigenous peoples across the world developed deep knowledge of their environments, managing game populations, practicing controlled burns, and planting in ways that preserved ecosystems for future generations. Even today, conservation efforts, national parks, and ecological restoration projects show humanity's ability to protect and heal. Humans plant trees as well as cut them, clean rivers as well as pollute them, and preserve species as well as endanger them. Our influence reaches into the air itself. By burning fossil fuels, humans have increased carbon dioxide levels beyond anything seen in hundreds of thousands of years. This change warms the climate, melts ice, and shifts weather patterns. At the same time, international agreements and technological innovations seek to curb emissions and transition to cleaner energy sources. The atmosphere becomes a canvas where humanity paints both harm and hope. The oceans too bear our mark. Overfishing has reduced some populations to a fraction of their former abundance, while plastic waste drifts in gyres across the seas. Yet humans have also established marine protected areas, restored coral reefs, and pioneered sustainable fishing practices. The ocean is a mirror of human duality, reflecting both exploitation and stewardship. Biodiversity tells the same story. Human activity has driven extinctions, clearing habitats, and introducing invasive species that disrupt ecosystems. And yet, humans have also worked to save species from the brink, reintroducing wolves to Yellowstone, protecting giant pandas in China, and creating seed banks that preserve the genetic heritage of crops and wild plants. The role of humans is not written in one direction. It is a pendulum that can swing toward destruction or toward care. In many ways, humans are like rivers, powerful, transformative, and capable of carving new channels through the landscape. But unlike rivers, we are aware of our influence. We can reflect on our choices, debate their consequences, and envision futures. That awareness gives us responsibility. We are not merely one species among many. We are architects of Earth's present and future. Culturally, humans have long recognized their ties to the natural world. Myths and stories often depict people as children of the earth, shaped from clay or born of trees. Religions and philosophies across time have taught respect for the planet as a source of life. Even in the most modern cities surrounded by steel and glass, parks and gardens remind us of our dependence on green spaces. Art, literature and music continually return to themes of nature, reflecting our deep-rooted connection to the land, water and sky. The paradox of humanity is that we are both destroyers and caretakers. We cut forests but also plant them. We pollute rivers but also clean them. We alter the climate but also strive to stabilize it. Our double role is not a contradiction so much as a reflection of our power. With great influence comes the ability to cause great harm, but also to create great healing. The future of Earth's living systems will depend not only on natural laws but also on human choices. When we look back on our role in Earth's story, it will not be measured only in monuments, machines, or megacities. It will also be measured in how we managed our relationship with the rest of life. Did we push ecosystems past their limits, or did we learn to live within them? Did we see ourselves as rulers of nature, or as part of it? These questions remain open, written into the decisions of each generation. To see humans as a force of nature is to recognize both our might and our vulnerability. We have altered the land, the sea, and the air, yet we remain dependent on the same cycles of water, soil, and oxygen as every other creature. Our power is real, but so is our reliance. Like forests and rivers, we are woven into the web of Earth's living systems, bound by the same rules of balance and resilience. The story of humans is not finished. We are still shaping Earth, still choosing between paths of disruption and care. The planet has endured catastrophes before, from impacts and eruptions to ice ages and extinctions, and it will endure long after us. What makes our era different is that, for the first time, one species can see its own influence clearly. Whether we act as caretakers or disruptors will determine not just the fate of ecosystems, but also the fate of ourselves. We are engineers of landscapes, builders of cities, and makers of machines. But above all, we are part of Earth's story, a force of nature, powerful and unpredictable, yet capable of reflection and responsibility. The question is not whether we will shape the planet. It is how and to what end. Earth today stands at a crossroads, a living planet facing both extraordinary resilience and profound fragility. It has survived asteroid impacts, volcanic winters, and ice ages, yet it now finds itself challenged by the actions of one species, humans. Climate change, biodiversity loss, and environmental degradation test the balance that has sustained life for billions of years. And yet, even amid crisis, there are glimpses of renewal, forests regrowing, species rebounding, and ecosystems healing when given the chance. Earth's story is one of tension between vulnerability and endurance, fragility and strength. The most urgent challenge of our time is climate change. By burning fossil fuels and releasing greenhouse gases, humans have thickened the atmospheric blanket that keeps Earth warm. Carbon dioxide levels, once stable for hundreds of thousands of years, have now risen to heights not seen in millions. This added insulation traps more heat, nudging temperatures upward across the globe. The effects ripple outward. Ice sheets melt, seas rise, storms intensify, and weather patterns shift. A world that once seemed predictable now feels restless, with extremes of drought, flood, heat, and cold becoming more frequent. Climate change also destabilizes the cycles on which societies depend. Crops struggle under heat waves and shifting rains. Fisheries falter as oceans warm and acidify, and wildfires spread across parched landscapes. The resilience of ecosystems is tested, and the safety nets of food, water, and shelter fray. For humans, climate change is not only an environmental issue but a social and economic one, affecting health, migration, and livelihoods. It reveals how deeply entwined we are with the planet's systems, how much our well-being depends on a balance we once assumed unshakable. Alongside climate change is the crisis of biodiversity loss. Species disappearing at a rate far higher than the natural background pace of extinction. Forests are cleared, wetlands drained, oceans overfished, and grasslands converted into farmland. Habitats shrink and fragment, leaving animals and plants stranded in pockets too small to sustain them. Pollinators that fertilize crops decline, predators vanish from ecosystems, and coral reefs bleach under warming seas. Each loss is more than a disappearance. It is a thread pulled from the web of life, weakening the fabric that supports all living things. Yet even as species vanish, others cling on with astonishing resilience. Whales once hunted nearly to extinction have slowly rebounded in some regions thanks to conservation efforts. Forests cleared by logging have regenerated when left undisturbed, with seedlings rising from the soil to rebuild the canopy. Wetlands once drained have been restored, bringing back birds, fish, and frogs. These examples remind us that life is not passive. Given the smallest chance, it rebounds, adapts, and flourishes. The crisis is real, but renewal is always possible. Earth's fragility is often easiest to see in sudden moments of collapse. A coral reef bleaches within weeks of high temperatures, turning from a kaleidoscope of colour to a ghostly white. A glacier retreats year by year, its vast mass dwindling before our eyes. A wildfire races through a forest, leaving only ash and silence. These events are stark reminders that ecosystems can reach tipping points, beyond which recovery is difficult or impossible. They highlight the delicacy of balance, the fine line between resilience and collapse. Yet Earth's resilience is no less real. Forests that burn often regrow, their seeds adapted to fire. Grasslands bounce back from drought, roots reaching deep into the soil. Even coral reefs, though severely stressed, can recover if waters cool and pressures ease. The planet's history is filled with cycles of destruction and renewal, with ecosystems reshaping themselves after upheaval. While the current crises are human-driven and faster than many natural shifts, they still unfold within a world that has endured worse and found ways to heal. The human role in this balance is pivotal. We are both the source of many crises and the agents of potential renewal. Renewable energy from wind and sun is replacing fossil fuels in many places, reducing emissions and offering cleaner air. Protected areas now cover large portions of land and sea, providing refuges where ecosystems can recover. Rewilding projects reintroduce species like wolves, beavers, and bison, restoring ecological processes that once shaped landscapes. Seed banks safeguard genetic diversity, ensuring crops and wild plants have a future even in uncertain times. These efforts show that humans can act as caretakers, not only disruptors, if choices are made with foresight and respect. Still, the challenges remain immense. Climate systems are slow to shift and carbon lingers in the atmosphere for centuries. Biodiversity once lost cannot easily be regained. The pace of human consumption often outstrips the pace of renewal. Yet even here, there is room for hope. The ozone layer, once threatened by human-made chemicals, is healing thanks to international agreements that curtailed their use. This success story shows that when humans act collectively, planetary-scale problems can be addressed. In many ways, Earth's crisis is also a mirror of humanity's choices. It reflects how we view our relationship with the planet, whether as conquerors extracting endlessly or as partners within a living system. The tension between fragility and resilience is not only about ecosystems, but about human societies themselves. Are we able to adapt, innovate, and act in ways that preserve the systems we depend on? Or will we press past the limits of resilience, leaving a diminished world for future generations? The glimpses of renewal are encouraging. Forests planted in degraded lands now stretch green again. Species once thought lost, such as the black-footed ferret or the kakapo parrot, cling to survival through dedicated conservation. Rivers once choked with pollution now run cleaner thanks to restoration. Even in cities, green spaces, rooftop gardens, and urban wetlands show that renewal is not confined to wilderness, but can flourish wherever life is given space. To think of Earth in crisis and renewal is to think of balance. The planet is neither indestructible nor fragile beyond hope. It bends, strains, and sometimes breaks, but it also rebuilds, reforms, and surprises with resilience. Its memory of catastrophe and recovery stretches back billions of years, and we are simply the latest participants in its ongoing story. For those who pause to consider Earth's condition, the message is not despair, but responsibility. The crises we face are daunting, yet they are also opportunities to reimagine our role as part of the planet's living systems. Renewal is possible, but it requires choice, patience, and humility. Earth is not just a backdrop for human life. It is an active participant, shaping and being shaped by all who dwell on it. The crises of today remind us of fragility, but the stories of renewal remind us of strength. Between these two truths lies the future, a living planet that can endure, adapt, and flourish if given the chance. To live in this moment is to stand at the edge of history, where crisis and renewal are not separate but intertwined, and where every action helps decide which story Earth will tell next. Earth is a planet in motion, never still, never finished. What we see today, continents, oceans, forests, deserts, and the creatures that inhabit them, is only one chapter in a story billions of years long. To imagine Earth's future is to stretch our minds beyond human timescales, into the slow rhythms of geology and the vast possibilities of evolution. The world we know will not remain as it is. Continents will drift, mountains will rise and erode, climates will shift, and life will continue to reinvent itself. Humanity may or may not endure, but Earth's story will go on. The continents are restless travellers. They move at only a few centimetres per year, yet given millions of years, these small steps add up to epic journeys. The Atlantic Ocean, now vast, will one day widen further before eventually beginning to close. Africa is inching northward into Europe, destined to raise new mountain ranges where the Mediterranean now lies. Australia is drifting toward Asia, while California creeps slowly along its fault lines, reshaping coastlines. Hundreds of millions of years from now, the continents may merge again into a new supercontinent, just as they have before in Pangaea and earlier in Rodinia. The face of Earth will look entirely different, but the process is familiar. Land and sea forever trade places, sculpting new environments and opportunities for life. As continents shift, so too will climates. A supercontinent at the equator may swelter under heat and dryness, while polar regions may become more temperate. Ocean currents will reorganize themselves around new coastlines, redistributing heat and altering rainfall. Deserts may expand where rain once fell, while new forests may emerge in regions now barren. Ice caps could wax and wane, seas could rise and fall, and ecosystems will adjust just as they always have. For Earth, climate is not fixed but cyclical, always seeking new balances as continents and atmospheres change. Life will continue its dance of adaptation. Just as the extinction of dinosaurs opened the door for mammals, so too will future upheavals give rise to new forms. Perhaps mammals will diversify further, or perhaps entirely different lineages will dominate. Insects, microbes, and fungi, already among the most resilient of organisms, will almost certainly thrive, evolving into new niches and unexpected forms. The oceans, which have always been crucibles of innovation, may harbour creatures as strange to us as trilobites and ammonites were to earlier ages. Evolution is restless, and as long as Earth provides energy, water, and chemistry, life will not stand still. Humans, of course, wonder about their place in this unfolding future. Will our species endure, adapting to shifting climates and environments as our ancestors once did? Or will we vanish, leaving only traces of cities and artifacts buried in sediment layers? In the grand sweep of Earth's history, even the mightiest species are temporary. Dinosaurs ruled for over 100 million years, yet their dominance ended abruptly. Mammoths, saber-toothed cats, and countless others once seemed eternal, but they are gone. Humanity may carve its mark deeply, but Earth's memory will eventually erode our monuments, scatter our buildings, and recycle our metals back into stone. What will remain is not human permanence but human influence, recorded in layers of rock and fossils as evidence of a species that reshaped the planet. Even if humans disappear, Earth will continue. Forests may reclaim cities, coral reefs may adapt to new seas, and animals will evolve into niches we never imagined. The scars of our activity, plastic residues, radioactive isotopes, and altered sediments will become part of the geological record, a signature of our time. Yet life itself will not end. It may take new forms, but it will carry on, just as it always has after upheaval. Earth's continuity lies not in the survival of any one species, but in the persistence of life as a whole. Looking further still, Earth's fate is tied to the Sun. In about 1 billion years, the Sun's gradual brightening will make Earth warmer, eventually evaporating oceans and transforming the planet into something less hospitable. In about 5 billion years, the Sun will swell into a red giant, engulfing Mercury and Venus, and possibly Earth itself. By then, our planet may no longer be habitable, its surface scorched and seas boiled away. But until that distant future, Earth will remain dynamic, shifting and reshaping itself countless times. Its living legacy will continue to evolve until the very end. There is something humbling in this perspective. It reminds us that Earth is not ours to keep, nor ours to control. We are participants in its story, not authors of its ending. Our presence may change the current chapter, but the book will go on, written in tectonic shifts, evolutionary experiments, and cycles of renewal. The mountains will rise and crumble whether we are here or not. Rivers will carve valleys long after our dams have failed. The winds will carry seeds, and the seas will foster life, whether human eyes remain to watch or not. And yet, within our brief moment on this planet, we have the ability to shape its near future. We cannot halt continental drift or solar evolution, but we can decide how we interact with Earth's living systems now. We can choose whether to accelerate extinctions or to foster biodiversity, whether to destabilize the climate or to preserve its balance. The far future may be beyond our control, but the next centuries are not. What legacy we leave will shape the opportunities for life after us, and perhaps for humanity itself if we endure. In this light, Earth's future is not only about geology and evolution, but about responsibility. We are the first species to understand the scale of planetary change, to see the fragility of ecosystems and the consequences of our actions. That awareness brings a choice, to live as caretakers of a planet that will outlast us, or to act as disruptors who shorten its cycles of renewal. Earth's continuity is a source of reassurance. It has survived impacts, eruptions, and extinctions. It will survive us too in one form or another. But this continuity is also a call to humility. Our buildings, borders, and inventions will one day fade, but the planet's rhythms will endure. The continents will drift, the seas will rise and fall, and life will continue its restless creativity. Earth's future is a living legacy, one that stretches far beyond humanity's horizon, reminding us that we are threads in a tapestry far older and greater than ourselves. To imagine Earth's future is not to imagine an ending, but a continuation. The planet will persist, restless and resilient, long after our time has passed. Mountains yet unborn will rise, forests yet unseen will spread. Creatures yet unimagined will walk, swim, and fly. The story will not stop with us. It will unfold, as it always has, in cycles of change and renewal. Earth's legacy is not just its past, but its promise, a living world forever in motion. Earth is not a static sphere of rock and water, but a breathing, living, ever-changing system. Its oceans circulate like veins, its forests rise and fall like lungs, its climate shifts with the slow inhale and exhale of ice ages and warm periods. From the fiery birth of continents to the quiet fall of leaves in autumn, the planet has always been in motion, always reshaping itself, always alive in ways both grand and subtle. Within this vast rhythm, humanity is but one heartbeat. Our fields and cities, our stories and struggles, all unfold within Earth's longer breath. We are part of its systems, dependent on its balance of water, air, soil, and light. The tides that move with the moon, the winds that sweep across continents, the rains that nurture crops, all of these remind us that we belong to a greater whole. It is humbling to remember that Earth was here long before us and will continue long after us. Yet this does not make our role smaller. If anything, it deepens its meaning. For a brief span, we are participants in this great living system. We can choose to move in harmony with its rhythms, to listen to its needs, and to recognize the beauty of its resilience. And so, as this journey across Earth comes to a close, let it settle in as more than facts and histories. Let it be a reminder of belonging, of continuity, and of the gentle truth that to live on Earth is to live within a breathing planet. As you rest tonight, picture the planet turning slowly beneath the stars, oceans sighing against the shore, forests exhaling into the sky. The same breath that has carried life for billions of years carries you too. May that thought bring calm, grounding, and a quiet sense of peace. The Earth is still breathing, and so are you.